to just do some introductions, just so that we can kind of get to know each other, especially because it's a small group. And so it's going to probably, if it's okay with you all, be super interactive, because I think that's going to be more fun and help you get the most out of this session. So Mandal, do you want to introduce yourself first? And am I saying your name correctly?
Oh, actually, it's like Aishi Mondal. The last name is first because I'm logging in through like my school account.
Oh, sorry about that.
Oh, it's okay.
So it's
Yeah,
Aishi?
yeah, Aishi.
Okay,
So
awesome.
my name's Aishi. I'm a senior in computer engineering at University of Illinois, Urbana-Champaign.
Awesome, awesome. Very cool. Why are you interested in artificial intelligence and data analytics and stuff like that? Is there a specific reason, or are you just kind of dipping your toe into it?
Currently I'm dipping my toes, but also I took like a couple electives junior year, and then I think I got really interested in it, especially having done a couple of projects using Python. So I
Uh-huh.
thought, this would be a good fun way to kind of get some real life applications of how the industry looks like, and then maybe see if I want to do this in the future.
Yeah, that's awesome. Great. Thank you. Dawson, what about you?
My name is Dawson. I'm here in Atlanta, Georgia. I'm actually just finished a boot camp with a company called Springboard into data analytics, kind
Uh-huh.
of changing careers and just try. The AI bus just came up, so I was like, hey, this looks like something of the future. So I really need to get as much knowledge about this as I can.
Yeah, that's awesome. So you said you just took a boot camp, and was that for like an intro data analytics? I just want to make sure I heard you correctly.
Yeah, it was like intro to data analytics. It was a 6 months boot camp, and I just got finished like a month ago. So kind of on the job hunt and looking at what's out there.
Okay, that's awesome. That's awesome. And if you all are interested, we can definitely spend part of the time at the end talking about like what does the job hunt for analytics jobs look like and stuff like that. Because that's some of the stuff that we cover in our SkillSpire courses, and I
Okay,
teach one of those, so I'm happy to like dedicate part of the discussion to that if that would be helpful for you all.
that sounds great.
Okay, awesome. And just out of curiosity, Dawson, what kinds of things did you learn in your boot camp?
Well, we started out doing a little bit of Excel, then we did Power BI, Tableau, Python, and SQL. Uh,
Okay, awesome.
it was challenging, it was intense, but I really it took me a ways. I learned a lot.
That's amazing. It sounds really similar to SkillSpire's Intro to Data Analytics class, which is the one that I teach, where we do very, very similar. We do Excel, we do SQL, we do Power BI, and we do Python. So it sounds pretty similar. So that's pretty cool.
Nice. Thank you.
Yeah, it's great to have you. Hey, Matt.
Thank you.
I saw we just had someone else log on. Matt, are you able to hear us?
Hey, sorry about that. I was in the other room getting the paper. How are you?
Doing great. How about you?
Apologize.
So we just did a round of kind of mini introductions if you want to introduce yourself.
Yeah, my name is Matt. Python. I learned Python on the job at a think tank. Had a great time doing it. Used it to analyze text data, mostly the pandas package, and then I think we used R to do some, community detection. It was a social media project related to analyzing white supremacist groups to determine which were most extreme.
Oh, wow.
Yeah, it was sponsored by the State Department. Really
Wow,
good.
wow. That sounds like very important work.
It was a real honor. The other people on the project were far more talented than I was.
Well, I don't know about that, but it sounds like a really, really cool project that it's awesome that you were working on. So great. And why are you interested in analytics? Was it just like in your job, it was kind of introduced to you and so you dipped your toe into it, or are you just trying to get like deeper into it in your career?
Uh, yeah, I don't know. I really did enjoy coding. It was a good time.
Mhm.
For me, it was helpful. I did it following a traumatic event, and so it was very helpful. And I think there's probably a lesson here that's universal. or has greater meaning. Following a traumatic event, it was very useful to be able to do something and have the computer spit it back and have feedback.
Mhm.
It taught me that I was able to actually do things again. And
Yeah.
so I had instant feedback when I was doing things wrong, when I was doing things right. And so that was really a helpful mechanism for coping.
Mhm.
And so I developed a positive association with coding and analytics.
That's awesome. Thank you so much for sharing. And I agree. I think that is somewhat of a universal experience, regardless of like our backgrounds or the things that have happened to us. But yeah, at least for me, like I have a very positive association with coding and programming and analytics for kind of similar reasons. So yeah, that's pretty cool.
Cool.
Okay.
Yeah, I mean, you asked about me. We should probably be talking about you. You're the one putting on the whole show, right?
Yes, sounds good. I gave a little mini introduction earlier, but I can just kind of go into a little more depth if you all want. So yeah, just the part that you missed, Matt. My name is Melanie, and I am a technology consultant at a company called Credera in Houston, Texas. And I also am a data science lecturer here at Skillspire. Okay, we have someone else, so I'll go ahead and admit them. I currently teach the Intro to Data Analytics class, where we cover Excel, we cover SQL or SQL, however you want to pronounce it. We cover Power BI, and we cover Python. And right now in the class that I'm teaching, we're doing Python, which I love. And then we also at Skillspire have some more courses like an advanced data analytics course if you want to go even deeper into Python and machine learning and all of that, which it sounds like you all might be interested in. But more about me, I really love analytics, I really love data science, and I really love statistics. And I discovered it when I was in college, which was super lucky. Because I just like had some good teachers who helped me see how awesome it was. And so I majored in information systems and I got a concentration in statistics and data science. And so I got super into it then. I did a research project which allowed me to use some of my coding skills and my statistics skills. And that was really the beginning of my love for analytics. And now here I am. So yeah, really excited to be here with you all. I see we have someone new. Is it Hund? Is that how I pronounce your name?
Yes.
Okay, awesome. Do you want to just give a quick introduction?
Yeah. My name is Hunde. My last name is Rufi and Rufi. Yeah. I want to participate on these events. I used to be the Skillspire trained last I think before 2 years or 1 year, and I want to see how this goes as well. That's why I showed up here.
Awesome. Sounds great. We're glad to have you. Okay, so let's go ahead and get started. I'm going to share my screen with some slides. And we can start there and then we'll jump into some Python later. So I'm going to do this and then flip my slides. Okay, awesome. Could I get someone to unmute and let me know if you can see them?
Yes, ma'am.
Awesome, thank you. Okay, let's get started. So I just introduced myself. As you know, I am a technology consultant and a data science lecturer. So about today, so for the next few hours, we're going to be covering these main things. But if there's other things you all want to talk about that are kind of related to this, feel free because the group is so small that we can really get out of this what we want to. So first, we're going to talk about artificial intelligence, and we're going to talk about it. We're going to start kind of abstract, and then we're going to drill down into what it really means and the things that we can do with it in industry. Then we are going to talk about machine learning, because I know there are probably like a wide array of experience levels with machine learning and artificial intelligence. So we're going to start with some of the basics, and we'll probably get a little more specific as we go. And then finally, we'll close out by working on some real machine learning algorithms in Python. And this is a beginner level course, and so we're going to start pretty basic, so don't worry if any of this sounds unfamiliar to you. And then we'll go from there. So first, let's talk about what is artificial intelligence. So artificial intelligence is essentially just the ability of computers to mimic or emulate human thought. And so artificial intelligence allows machines to perform tasks that human beings might perform in real world environments. So we say that these machines are intelligent, but we tend to put this in quotation marks because what does intelligence really mean if not talking about human beings? But when we talk about this intelligence, what we're referring to is the ability of machines or of computers to perform tasks without explicitly being told what to do by humans. But as you might know, or as you might guess, this requires a lot of training of algorithms and such by human beings in order for this to function. And if you have any questions or anything, feel free to just unmute and interrupt at any point. So I just wanted to talk about some examples of AI first, but I wanted to see if anyone had any that they wanted to bring up before I mentioned the ones that I was going to show and talk about. So does anyone know of any cool industry or real world examples of AI?
ChatGPT.
ChatGPT, exactly. Yeah, one of our favorites. Do you use ChatGPT?
Yeah, sometimes. I think it has been useful for me, especially in studying. So if I'm going through something and I really don't understand, I think it's a great quick way to just ask questions and get immediate answers instead of, having to search the whole web or go through, YouTube videos and try to find what you're looking for. And also I feel like it's a lot more convenient and quick.
Yeah, I agree. And actually, thank you for bringing that up because that was my first example. Yeah, that's great. I think ChatGPT is really rising in popularity too, and along with Bing's and Google Bard. And there's even these new concepts coming out called prompt engineering, where we can start to give ChatGPT or these similar AI systems better prompts to get better results. And so there's tons of articles about prompt engineering if you're ever interested in looking at that, and maybe even I can pull some up and show you. But it's how we can really get the most out of ChatGPT and these similar AI systems. So yeah, this is definitely one of my favorite and one of the ones that I use most frequently. I know I have ChatGPT bookmarked on my Chrome because I use it very, very frequently. So definitely a big fan of that. Another one I was thinking of was Amazon Alexa. So does anyone use Amazon Alexa or a similar system to that who has experience with it? Yeah, I don't either, but it's just one of the canonical examples of AI. Does anyone else have any examples? I saw maybe Dawson had unmuted themselves, but I wasn't quite sure.
I have used this one called Beautiful AI to help with some presentations. I mean, I use ChatGPT frequently all the time. I've interchanged and used Google Bard also, just to see what what the difference is between both of them. But yeah, I've tested out quite a bit of them.
Oh, cool. And what did you notice were any of the differences between ChatGPT and Google Bard?
Google Bard has more up-to-date information, but it's wrong more often than ChatGPT.
Okay, that's pretty cool. Thank you. That's great. And you said Beautiful AI. Can you talk a little more about that? I've never heard of it.
Beautiful AI kind of helps you with presentations, so like PowerPoint presentations. So you could actually do the PowerPoint and upload it, and it will give you suggestions and hey, what if you should do this, if you should do that. In some instances, if you pay, I've only used the free version, but you can use the paid version that can actually do an entire presentation for you.
That is very, very cool. Maybe I could have used that for today. That's awesome. Really cool. Any other examples that we can think of? Okay, I will keep going, but if you have any more examples, feel free to jump in. We also have facial recognition technology. So I unlock my phone, and probably a lot of you do too, just by showing it my face, and it uses artificial intelligence to recognize that as my face. We have recommendation engines by some of our favorite music streaming apps like Apple Music and Spotify. And so, yeah, these recommendation engines are examples of machine learning, which is a category of artificial intelligence, as we'll discuss later. which are able to use the songs that we listen to and come up with even better songs. So just out of curiosity, do any of you use either Apple Music or Spotify or both?
Apple Music for me.
Apple Music? How do you feel about Apple Music's recommendations for you in terms of your music?
But it's not really good for me because the type of music that I listen to, I'm actually not. I listen to like calypso and soca music, so I don't get a lot of recommendations from them for that. But like when I listen to certain music like R&B and hip hop, I do. But the music I listen to most of the time, not really. And I guess it's because there's not a huge library of that type of stuff on Apple Music.
Right, that makes sense. So when like our sample size or the amount of data that we have is small, it's harder for it to make good recommendations
Yes.
because there's such a limited pool of data. Yeah, cool. Anyone else use either Spotify or Apple Music? Or a similar app?
Yeah, I use Spotify actually.
How do you feel about its recommendation engine?
I think it's pretty good. I think most of the time though, I end up just listening to my own like playlist, which I've already, kept aside. But I do like the feature where they usually have like a weekly playlist, and then they have something similar to other artists, or they have something like the same artist but different songs if they have different genres. So I like that they have, different types of recommendations, and they keep like generating it. One thing which I actually found pretty cool was I have listened to music in like multiple different languages. So even if it is like the same genre but different languages, they are able to like make that into one playlist. So I think that was actually pretty unique.
Yeah, that is pretty cool. That's awesome.
Yeah.
Yeah, and from what I understand and what I've heard, I believe that Spotify's recommendation engine might be a little bit better than Apple Music's, at least right now. Just in terms, maybe it's because they have more songs than Apple Music does, and so when we have a lot more data, it's easier to make better algorithms. But that's just what I've heard and what I've experienced as well. But I have Apple Music because I share the account with multiple people, and it's not worth it to me to switch over. So I still have Apple Music despite my belief that Spotify's engine is a little bit better. Very cool, very cool. We also have autonomous vehicles, which use artificial intelligence to kind of gauge their surroundings and start to make intelligent decisions about where to drive, when to stop, how to change lanes, etc. Siri, of course. Hey Siri, canonical artificial intelligence. My Apple phone actually just turned on when I said that. Yeah, a canonical example of how we use AI in our everyday life. Although I would say, at least for me, ChatGPT is starting to kind of reduce my need for Siri. And also another kind of more fun example is NPCs in video games. And so we can interact with people that are not real people in video games, for example. And that would be another example of AI. Did anyone think of anything else? Okay, let's keep going. So who is this? I'm going to need someone to unmute because I can sit here in the awkward silence for a long time.
Oh, Steve Jobs.
Yes, amazing. Steve Jobs. And so, despite what the long silence might suggest, probably most of you recognize this individual very quickly, probably the second that I moved the slide onto this one. So we as human beings can recognize that this is Steve Jobs. But how did our brain do that? So without even realizing it, what our brains do is we look at the facial features. We look at, for example, how far is the space between the eyes of that individual. We look at whether they have glasses and what type of glasses. We look at their hairstyle, the hair thickness, the clothes like the black turtleneck, and millions of other features. And our brains are able to instantly decide who this person is if we recognize them. So the question is, and the ultimate question of artificial intelligence is, can we train a machine to think in the same way that we think? And of course, the answer is yes, because that is artificial intelligence. So an example of seeing this in action that we can just take a look at very quickly is I just clicked on this button, which I have hyperlinked to Google Images. And I am going to, let's see, go back to these slides. And I'm just going to copy this image. And let's do a reverse image search on Google Images. So I'm going to hit search by image, and I will paste my image right here. And instantly, we get from our search engine that this is Steve Jobs. Even though I got this image from a source that wasn't Google Images, because it's able to recognize the features of this individual's face and instantly almost instantly figure out who that is. And then we also get Tim Cook, a different CEO of Apple at a later time. Because that's a related person and it recognizes that. So that's kind of a fun example of how we can use AI in really simple ways and kind of connecting it to the way that we as human beings think. Okay, so let's talk about the types of artificial intelligence. So there are three types of AI. Does anyone know what they are? Okay, so oh, go ahead.
Nope, no, you're doing, you know better. Go.
Okay, sounds good, sounds good. But if there's inputs at any point, feel free because we can make this as conversational as we like. So the first kind is called narrow AI. And this is what most of the AI that we deal with is. So this is AI that's designed to perform specific tasks such as our voice assistants like Siri, image recognition, recommendation systems like the ones on Spotify or Netflix that recommend songs or shows. There's also general AI, and a lot less of the AI that we deal with, especially we as just common consumers deal with, is general AI. So this is when AI has nearly human level intelligence, and it's able to understand things, to learn things, to perform things that human beings can also do. And then finally, the third category, which it's a little dubious that this is considered a category, but it is nonetheless, is super intelligent AI. And this is when AI surpasses human intelligence. But this is like mostly fictional and often depicted in science fiction right now. I think it's just kind of considered a category right now, despite the fact that like we don't really categorize AI that currently exists into this category. So like I mentioned, narrow AI is by far the most common form of AI and the one that basically the only one that we interact with. So even AI, which seems really powerful, like ChatGPT, is still considered narrow AI. And just to give you an example, I told ChatGPT to make me a presentation about an introduction to AI, and it gave me the slide that I just showed you about the three types of artificial intelligence. So yeah, it's pretty cool. Even narrow AI, which is, of course, the most primitive category of AI, is extremely, extremely powerful and can do a lot of cool things for us. And the reason that ChatGPT is considered narrow AI, even though we can do a lot of things with it and we can converse with it, is because it's really only specifically designed for one task, which is language processing tasks. And so it seems like that's a lot, and it is, and it's super, super cool, and I love it, but it is still like a pretty specific task. Any questions so far?
So when you said types, I guess I I hadn't heard really of these. Where does like machine learning and deep learning fit into the scope of these three examples?
Yeah, and I'm glad you asked. Usually in narrow AI, because usually, and it kind of depends, but a lot of machine learning tasks are for pretty specific things. So we'll have an algorithm that performs a specific kind of prediction, for example. And so that would usually be considered narrow AI.
Oh, sounds good. Thanks.
Great question. Any other questions? All right. So let's talk about how artificial intelligence works. So first, we have philosophy. And we're going to start abstract, and then, like I promised, we will get a lot more practical as we go. But in terms of philosophy, human beings use philosophy to better understand our actions or why we do things. So often in the field of philosophy, and I took some philosophy classes in college and they were super fun. And we were always asking, like, why are we doing this? Or why do human beings act in this way? Which helps us make better decisions. And so this is applied to AI by using the various philosophical approaches that we can embed in our algorithms in machine learning, for example, to help machines make what we would consider to be the right decisions. And it's not necessarily that the machine knows, okay, this is a right decision. It simply mirrors the way that a human being might think and behave. Okay, so the next thing is math. And so machines need to use logic, they use computation, they use tons of probability, and they do this to solve problems. And so math is a big component of the way that AI works. And so is economics. And when I think of economics, I think of like money, but economics is a little more than that. It's really the study of how people make choices according to their preferred outcomes. And so we can use important economic concepts like design theory and Markov decision processes to help build intelligent systems with different techniques from economics. As you can imagine, neuroscience is really heavily connected to artificial intelligence because neuroscience is just the study of how brains function. And since AI is trying to replicate how brains function, it's just pretty easy to see how those overlap. So in general, computers are a lot faster than the human brain, but the human brain still actually has more storage capacity and interconnections than computers do. And so what a lot of computer scientists are trying to do with AI right now is kind of narrow that gap. Psychology as well is a big component of how artificial intelligence works. And so with psychology, we try and understand how our brain reacts to its environment. And so we've actually codified in AI many cognitive theories of psychology to build algorithms that can power different technologies. So for example, with AI chatbots, we've codified cognitive theories in terms of like how it's appropriate to interact with people and manners and things like that to fuel AI chatbots and the way that they respond. We also have computer engineering, and this is very, very, very important for AI because it's how we translate all of our theories and our concepts, which has been basically everything we've talked about up to now, into machine-readable languages that design the algorithms themselves. We also have control theory. So intelligent systems need to be able to modify their actions to produce the desired output. So in other words, they need to learn how to control their actions to optimize behavior because we want our algorithms and we want our technologies to keep improving over time. And to do that, they need to control their actions. And finally, linguistics. And so the reason I included this is because all of our thought and the way that we think, at least the way that we understand it right now, is that it's based on some language. And so machines need to be able to understand language to understand how human beings think. And that's more than just sentence structure, although of course sentence structure is an important part of it. But it also requires us to teach these machines the subject matter and the context of the way that we speak and think. So this is kind of like an abstract representation of how AI functions and all of the different components that go into it. Are there any questions or any elements that people would like to add? Okay, so now we are going to pivot into machine learning because as you probably know, in order to understand anything further about how AI works, like if we want to stop dealing with these like abstract bubbles and start talking about the nitty-gritty of how AI works, we need to talk about machine learning. So what is machine learning? Machine learning is the way I like to think about it, and I got this from Columbia Engineering. It's just a pathway to artificial intelligence. And so as you can see, artificial intelligence is this big category right here. And then machine learning is a subcategory of AI. And it's the how of AI. It's how we make AI work, or one of the big ways that we can make AI work. And so with ML, we use algorithms to train computers how to automatically learn and recognize patterns from data so that they can make increasingly better decisions. And so when I was talking about control theory on the previous slide, this is kind of what I was talking about. We need to use data in order to train our algorithms on our computers to get better and better and better. And that's why machine learning is so effective, because it's more than just running a piece of code and then us going back and fixing our piece of code and then running it again, and then fixing our piece of code and running it again. With machine learning, our algorithms improve over time. So in simple terms, this is a graphic that I really like to visualize machine learning. We have some historical data, which is data that's just already been collected. We process and we analyze that data, and then we create models or algorithms from that data in order to do things like making predictions. So there are three main types of machine learning, and I think maybe even someone already mentioned them earlier. And the first kind is supervised learning. So with supervised learning, we use input data and corresponding output data to learn from examples and make predictions about new data accurately. So what this means is that we have our input data, and this input data is labeled with the correct categories, for example. And then we have our output data. And so we use our input data in order to train models and test models and make them really good. And then we use the output data in order to evaluate whether those inputs were correct. And so it's able to learn from that, and it's able to make predictions about new sets of data after we make our models on the input and output data. We also have, and we're going to go really in depth into these. This is just kind of an introduction. We also have unsupervised learning. And with unsupervised learning, this is data where we have the input data, but there's not really a specific output variable. And so in unsupervised learning, we allow our machine to start discovering patterns and features without telling it what we're really looking for. And then once it creates a model based on that, we can apply new data to that algorithm to make predictions pretty accurately. And so unsupervised learning, we have the input data, but we're not defining our output variable. And then finally, and we're not really going to talk about this in this workshop because it's a bit more advanced, but we have reinforcement learning. And reinforcement learning is just when a computer program interacts with an environment and it gets usually rewards, but sometimes punishments that train it over time. And so you can kind of think about training a dog, and when the dog does its trick correctly, you give it a treat. And so it's kind of trained over time to keep wanting that treat, and so it keeps improving. Have any of you heard of these categories before or interacted with them?
I've heard of the first two.
Awesome. Have you ever used any of the techniques in these categories, or is it more of like you've just kind of heard of it?
I just kind of heard of it, just read about it, while, doing my, research about AI, but never really did any of it.
Right. Okay, cool. No worries, because today we are going to dive into some of them. We're going to do some examples from supervised and from unsupervised learning.
Oh, nice.
Anyone else?
I think I've heard of the first one, because we did like Bayesian statistics for one of like my probability courses and stuff. And I think they mentioned that this could be very useful for like supervised learning in Bayesian modeling. So I've heard of like the application, but I've never really like done it.
Exactly. Yeah. The Bayesian probabilities and things like that are very useful in supervised learning. Exactly. Awesome. Anyone else? And Aisha, you said you did computer engineering, right?
Yeah.
Very, very cool.
Major
Awesome.
in computer engineering.
That is amazing. So I bet a lot of these things are going to be super applicable to your major too.
Yeah. That's the plan, hopefully.
That's awesome. Cool. Anyone else? Okay. So let's just kind of start diving in a little deeper. Since we have a little bit of knowledge about these categories, but we want to kind of drill down and make them make more sense. So with supervised learning, this is the one where we have the labeled input data, and we also have our output data. So let me tell you what that means if that still sounds confusing. So let's say that we have some pictures of dogs and cats. That's our data. It's images of dogs and cats. And maybe we have like thousands of these images. So with supervised learning, we need to first, with some of our data that we're using to train our model, we need to tell our computer which images are dogs and which images are cats. So that's what I mean by the data is labeled. Another example, if we weren't doing dogs and cats, would be, let's say we are trying to predict like housing prices. We would have to give the housing prices of the houses to train the model with other characteristics like the zip code and the number of floors and the number of rooms and things like that. But then when we have new data, we can apply that when we don't know the output variable and still have a good model. But to make the model, we need to know what category it falls into that we're trying to predict. So we have cats and dogs, and we have these images, and we tell our computer first, or our machine first, whether these images are cats or dogs. So then it trains the model, and it looks at different characteristics of these images because it already knows which ones are cats and dogs. So it looks at all the cats, and it figures out, how am I going to predict whether a new image is a cat? And it figures that out. And it says, okay, how am I going to figure out if a new image is a dog? And it figures that out. So we have a model now. So that's in the model training. Then we move on to prediction. And with prediction, we have new data, completely new data. And with this new data, we don't know whether the image is a dog or a cat, because that's kind of the whole point of prediction with new data. And so based on the model that we've already created with the labeled data, we now have unlabeled data that we can make predictions about. And so now it gets this new image. And our model says, okay, what kind of image is this? And it classifies it as a cat. So that's kind of how supervised learning works. We have labeled input data and then unlabeled new data that we make predictions about. Are there any questions about how this works, or is there a part that anyone wants me to repeat? Okay, and actually, I have a slide hidden here, but I think because this was like a beginner course, but I think maybe there might be some people who would be interested to see some of this too. So we were just on this slide, so I've just unhidden this slide. But this is a little bit more of an in-depth explanation of how supervised learning works. So like I mentioned, we have our labeled data set. So the first thing that we do is we split our labeled data set into two categories. We have training data and we have testing data. And so our labeled data set is, say, the images of the cats and the dogs. And so we kind of shuffle up that data. So we mix up all the data so it's in a random order, and then we split it. So we take maybe like 70% of our data, and that will go in our training data. And then we have maybe like 30% of the data, the remaining portion, and that will be our testing data. So first, let's talk about this training data. So with the training data, we make our model. That's what we use to create the original model. So we have like 70% of our labeled data set of images of cats and dogs, and we use that to make our model. And so from that, we can test our model with the testing data. So we use the rest of our data that we have that's labeled, and we put that data in, and then we are able to see the accuracy rate on the testing data. And so what that does is it allows us to kind of get a gauge for how accurate our model might be before we apply it to new unlabeled data. So this split into training and testing data is one of the most important concepts in supervised learning, because we really use it in all supervised learning. And we can get even more complicated than that. There are even more complicated approaches we can do. But if you've never done supervised learning before, the main takeaway I want you to take from this graphic is that in order to train our model, we have to split our original data set that we're using into two chunks, the training data and the testing data. And we use the training data to make our model, and we use the testing data to evaluate our model. And then from there, if we figure out from the testing data and the evaluation there that our model is bad, we can go back and make a new model. We can change the features of our model. There are a lot of things we can do to improve it until we get a good model that we are ready to deploy and make predictions on with this unlabeled data. Any questions on that? Has anyone ever heard of the training testing split before?
First time for me.
Okay, cool. That sounds good. And I'm going to show you how to do this in Python too. So get ready. It'll be super fun. Okay, so now let's talk about unsupervised learning. So in unsupervised learning, we don't tell the machine what categories the input data falls into. So here we have apples and watermelons. So remember, when we did supervised learning, we had to tell the computer whether the images were cats or dogs. Here, we don't tell the computer whether these are apples or watermelons. We let it figure it out. So we give our computer this input data, and then we apply a certain model, and the model that we choose is kind of dependent on the data and what we're kind of looking to do. And then it's able to kind of classify these input data points into outputs. So we don't say whether these are apples or watermelons. We apply our model, and it categorizes these into apples and watermelons based on the characteristics. And so as you can see, this can be a pretty powerful thing. We also usually have to have pretty good data in order to be able to do this, because I mean, let's say it's something else, maybe like apples and peaches, which look a lot more similar than apples and watermelons do. As you can see, it might be kind of tricky for a computer to be able to discern a peach from an apple, especially maybe if the images were in black and white or something like that. And so, yeah, there are some limitations on this, but it's a really, really powerful thing. And again, let me just unhide this slide so we can go look at this. So here, as you can see in unsupervised learning, we don't actually use the training and the testing split. And the reason that we don't do that is because we don't know necessarily what categories these fall into. And so we can't like train our model and then test it and figure out our accuracy rate, because if we don't have the labels for those categories, we don't know how to say how accurate it is. And so here we just have our unlabeled data set. We train a model. The model identifies the hidden patterns, and then we can apply that to new data. And so this can be really awesome for clustering, for example. And we're going to do an example of clustering, with the most popular form being k-means clustering. Recommendation systems can sometimes be unsupervised. Also, principal component analysis, if you've ever taken like a linear algebra class or anything like that, falls into unsupervised learning, or a lot of its applications like dimensionality reduction do. And also sometimes anomaly detection, which is figuring out if something is weird with the data or if there's a big outlier. That can also fall into unsupervised learning. Okay, and then finally, we can go ahead and actually just talk about these, since I think we all seem to be at a pretty good place to talk about this. Let's just talk really quickly about reinforcement learning. So with reinforcement learning, kind of a way that we can think about it is, let's say that we have a bunch of shape data. So we have like circles and triangles and squares, and we give a shape to our algorithm. And we don't have like a data set like we did here. We don't have a bunch of input data. We're just kind of like one at a time. This new data comes in. The algorithm takes it in, and it identifies it as a square. So we give the algorithm a reward, and it's trained to kind of recognize whether it's a reward or a punishment. Then we get a new data in. Let's say it's a triangle. Okay, the algorithm says that that's a square. No, it gets punished. And so as you can imagine, it's kind of like training a dog, but it can be pretty powerful because you don't need a lot of like input data to train your model with. And so this is kind of like a theoretical way that we can think about reinforcement learning, because the algorithm is just kind of out in the environment receiving inputs in real time, and it receives rewards in order to improve. So we're not really going to go into it because we need to be a lot more solid on supervised and unsupervised learning before we talk about reinforcement learning. But just in case you want to do some more research on it or just know a little bit about it, that's kind of an overall summary of what reinforcement learning is. So let's just go and compare these three types really quick. So we have supervised, unsupervised, and reinforcement learning. So in terms of the data set, supervised learning, as we know, requires a labeled data set. And just to make sure you all understand, can someone summarize to me very quickly what a labeled data set means?
It's a data set where the identities of each of the members of the data set have a clear label. There's really no better word for it.
Exactly, exactly. Yeah, it's when we know the label or exactly of the input data. That's perfect. And then with unsupervised learning, the algorithm learns by identifying hidden data patterns from an unlabeled data set. So here we're not saying it's apples, it's watermelons. We're just letting it kind of figure it out based on the shape, based on the color. And it doesn't necessarily know, oh, that's a watermelon. It just knows to distinguish the watermelon from the apple. Okay, and then with reinforcement learning, we don't require data to train any sort of model. It just learns by interacting with the environment. Okay, and then in terms of learning, so supervised models learn by instructions. So we kind of tell the model, we say, okay, these are the cats, these are the dogs. If it gets it wrong, we probably train it again. And so we're kind of giving that algorithm pretty direct instructions on how to get better. With unsupervised learning, it learns by reasoning. And so it's able to kind of group these into watermelons and into the fruits into watermelons and into apples based on reasoning. So it's kind of looking to try and group things by similarities and reasoning that out. And then reinforcement learning just learns by experience because it's just out there in the environment. If it identifies the square correctly, boom, reward, that's experience. Okay, and then objective. So the objective of supervised learning is to learn one type of task to predict outcomes for new data in the same domain. So yeah, I think maybe the cats and dogs example is a good one for now. If we're training our model to predict whether new images are of cats or of dogs, we can't suddenly throw a parrot into that data set and expect it to correctly identify that because we're only really dealing with cats and dogs in that model. Or say we can't ask it to start predicting housing prices because it's just doing cats and dogs. So that's kind of what we mean. And then with unsupervised learning, we're trying to predict if new data is part of a cluster or an anomaly. And so we're grouping these fruits, for example, into different groups. So we have the apples and the watermelons, and maybe we have more data like oranges and pears. And so we're trying to figure out, does a new data point similarly identify with any of those groups? Or is it an anomaly, which basically means an outlier, like it's not part of any of those clusters? And then finally, we have reinforcement learning, which is goal-oriented because it wants to maximize its future rewards, which interestingly is an economics concept. And so it can handle new scenarios that it's never encountered before, whereas like we were talking about with supervised and unsupervised learning, they can't really handle new scenarios. So with supervised learning, yeah, we throw in a parrot, no, like it's not going to be able to identify that. With unsupervised learning, we might be able to tell if there's an outlier or an anomaly, and we probably will, but we won't be able to identify that no matter how many times we put that new data in. But with reinforcement learning, over time, it's able to handle new scenarios. And then let's talk about some algorithms for these. So for supervised learning, some of the most common algorithms are classification and regression. Has anyone ever heard of either regression or classification? Or actually like run them before?
Like linear regression?
Exactly, like linear regression.
I've done that too, but I've heard of it, but not the others.
Yeah, regression is interesting and classification too, because sometimes we think of these as statistical techniques, and they absolutely are, but we can use these statistical techniques in machine learning. Anyone else? Okay, and then with unsupervised learning, some common things, and we talked about this kind of on a previous slide, but there's clustering, which is grouping. It's grouping data points into different clusters or groups. So if we have different fruit types, yeah, we are grouping them into the watermelons, the apples, the pears, the peaches, things like that. and it just kind of groups them into data clusters on a graph. We have association, which is trying to figure out, for example, like the data points that are kind of close to other data points. We have anomaly detection, which is figuring out if there's an outlier or something wrong. We have dimensionality reduction, which is an application of principal component analysis, which is a little bit more complex, so I'm not going to get super into that. And then with reinforcement learning, some algorithms are, for example, the deep Q network, state action rewards state action, which probably sounds kind of familiar because from one of the previous diagrams. But again, we're not really going to get into those algorithms. I just wanted to give you some of their names in case you wanted to do some research or anything like that. So are there any questions? Okay.
Yeah.
Oh, yeah,
sorry.
go for it.
So the brittleness of the system, maybe more brittle left, less brittle right.
Could you explain what you mean by that?
Whether the model can handle, it's literally whether the model breaks if something is different.
Exactly. It's exactly like that. Yeah, that's a good way of thinking about it. Any other questions? Okay, so now what we're gonna do is, so we're gonna take a break because I know these workshops can be kind of long, and at least in my experience, having like multiple hours of things like talked at me on a screen on Zoom can just be so like draining. And so we are going to take a break. But before we do that, let's get our Python environment set up. And we are going to be using an online tool called Google Colab, just in case you don't have Python like set up on your computer or like installed on your computer. And so we are going to, let me get you a link really quick.
Quick question. If I have Jupyter notebook set up, can I use that?
Yeah, you should be able to use that. The code I'm going to give you is in a Google Colab, but it's the same file type, and so you should be able to use it in Jupyter.
Oh, I'll see.
Like, I don't think it should be a problem. Okay, so I will copy this link, and let me stop sharing my screen really quick. Okay, so I've given you a link to a Google Drive folder, and in that Google Drive folder, I have two data sets, one about USA housing and one about bank customer churn. And I also have a notebook containing some code. And the reason I've contained the code is if you want to, you are able to code along with me when we're going through the next section. But if you want to, you can just run this code, like if you don't have any Python background, because it's not assumed for this workshop that you know any Python, especially like more advanced Python that we need in order to run algorithms. So what we're kind of doing is just showing the conceptual backgrounds of some of these algorithms that we are going to run. So that's kind of the goal, but we also have some code that we're going to do it with. So if you can download these three files, does everyone have access to that folder?
Yes, I'm downloading them now.
Awesome. Okay, and then I'll share my screen. So the next thing you're going to do, you can just type in like Google Colab like this and hit enter. And then you're going to click on the welcome to Collaboratory. And then I think you probably need to like sign in with an email account. Maybe I should make an incognito tab so I can see what you all see because I'm already signed in. So here we click Welcome to Collaboratory. And then do you all see this screen when you get onto Google Colab?
Yes.
Okay, cool. So, okay, yeah, you have to sign in at this point. So I'll just go back to my other tab where I am signed in. So here, in files, you can hit file at the top, upload notebook, and then you can upload that notebook file that you downloaded from my Google Drive folder. And so that's how you can upload the file there. So you'll hit file, upload notebook, choose file, and then go like choose the file to upload. And then for the two data sets, you're just going to click on the upload to session storage button. So you're going to click there, and then you can go navigate to those, the two CSV files there. And so that's how you're going to do that. So you hit file upload to get the whole notebook in. And then to get the two CSVs, you will just click on that upload to session storage button. So I will go ahead and do that. Okay, I already have them in actually. So something to note here, because of the way this works in the cloud, is these files will only stay for your session. So it's like a certain amount of time. So after a certain amount of time, if you're not using it, these files will go away. So just make sure that they're still saved on your local computer so that you can re-add them later if you want to. For example, like if I close this and open it up tomorrow, these will, like my entire notebook will still be here, but these files won't be here. So I would have to re-upload these two CSV files. Okay. Was everyone able to get to that point where they have the two CSV files in their folder and then they have the notebook uploaded as well? Tunde, did you have a question?
Sorry. Thank you for your presentation. I like it. It's really good. I'm kind of urgently gonna leave. Is that are you gonna pause the record? Is that possible to do that?
To post the recording?
Yes.
Yeah, I'll have to check with the administration because I usually don't handle that side of things. But if it's being recorded, probably the recording will be sent out.
Yeah, I can see it is someone started recording, so I prefer that to be sent to my email if it's possible, because I'm urgently gonna leave now. Thank you for your presentation, though.
Okay, thank you, Hyundai.
Okay, thank you very much.
Okay, Matt, Aishi, and Dawson, were you able to get the files in?
Yep.
Yep. Cool, cool. What about you, Dawson? Okay, maybe Dawson had to step away for a second. Okay, so what we're gonna do now is let's take a 30-minute break just to take a little brain break because we're gonna do some coding after. And again, no worries if you don't have tons of coding experience because we'll keep it at a pretty basic level. But yeah, when we come back, we will start working with these files. And also, if you have any questions about the conceptual part, feel free to let me know then. So I'm gonna put a message in the chat so we know what time we're meeting back. Actually, are all of us in Central Time?
Eastern.
Eastern. Okay, so I'm gonna say let's meet back at 35 after the hour. So that's gonna be in 30 minutes. Sound good?
Sounds great. Thank you.
Awesome. Okay, see you back in 30 minutes.
Hey, Dawson, are you there?
Hey, Matt. I maybe Dawson is still on break, but I'm here.
Oh, yeah, I was just gonna, I don't know if Dawson is a he or a she. I was just gonna say, whatever, I don't know. They, I guess, is another thing now, um, which sounds bigoted, but not. Just trying to cover all the bases. Just trying to say the hand is up. That's all.
Mhm. Oh, okay.
Stop.
Oh, yeah. I think maybe that's from earlier. That's a good point.
Happens all the time in Teams meetings.
Yes, I am a big culprit of that.
You're doing really well, by the way. Very intelligent.
Thank you, Matt. Thank you. So you mentioned that you've done like I think you said language processing, and actually I can get my camera on. And some things like that before. What kind of job do you do?
Oh, currently,
Mhm.
a technical editor slash scientist slash chemist slash environmental scientist at a consulting firm.
Oh, that's very cool. That is a lot of things.
Yeah, I think it's a catch-all to just try and find. So it's billable hours. So it's a catch-all to just try and bill out the day. You know what I mean?
Right, exactly.
I really
Very
wish I could get away from the billable hours model, but what I do have to say is the people at that company overall have been very good.
Yeah, I too have critiques with the billable hour model, but it is what it is.
Yeah, wouldn't it be nice to have a salary that didn't require billable hours, man? Yours is billable?
With SkillSpire, no, because I am just an instructor here, but with my consulting job, yeah, it's billable.
Ugh, I feel for you. Makes life tough.
Yes, yes. Um, Very cool. So it seems like you have a lot of experience with machine learning. So do you feel you're still like getting some things out of talking about like some of these conceptual things and going through the code, or is there anything else that you also were hoping to get out of today? Just so we can make sure, especially because it's a small group, we can talk about whatever we want to talk about.
No, I mean, no, everything is going really well, and whatever works best for the group is good for me. And I don't have a lot of experience with it. What I've done is community detection, some clustering stuff,
Hmm.
and someone else had written a model for grading the dark triad scores of text, which was pretty cool, which I just sort of adapted. And then I did something, um, not really machine learning. Anyway, I'm not by training a mathematician or a statistician like you. My great fortune in education came in chemistry, and I devoted myself to it. Uh, Managed to have a pretty incredible aha moment and invent something cool.
Hmm.
But the academic system found a way to transfer that to my boss rather than to me. So initially the story was, for 20 years, he literally admitted it himself. He said, for 20 years, I've been saying the exact opposite in the literature. But when it came time to assign ownership in the patent, it was all his idea.
Hmm. Wait, for the invention that you created?
Yeah, I don't want to go into it. It's
Okay, okay.
life is really complicated. Anyway, what happened there is the experience soured my love for what I was trained in.
Mm.
Um, I was fortunate to find a startup that I worked for a little while, which was questionable at best, but
Hmm.
led me to um, a bunch of different things, and one of them led me to a consulting firm. So I got really lucky there. At the firm, there were I had it was a place to learn.
Yeah, very cool. You mentioned you did like some dark triad text detection. Is that referring to like Machiavellianism and things like that? Is that what you meant?
Yeah, that's how we graded the text from. So I pulled data from Telegram. I adapted someone else's Python script
Hmm.
to pull data from Telegram. We used some Brandwatch, I think it was called at the time, to pull data from Twitter. We pulled data from white supremacist message boards. We wrote custom scripts for that. What else? Reddit. which was done by keyword.
Mm.
And then we used, so for the platforms where you could do it, we used a snowball approach. So you pick, I think I picked like 20 white supremacist groups, and then anyone they at gets added to the next hop, and you do like
Right.
4. And then the text is graded for Machiavellianism, narcissism, and I can't remember what the third of the dark triad is.
I think it's psychopathy. I took a class where we covered this at one point.
Yeah, it was phenomenally interesting. It was an approach that we brought in from the literature, and we used those to grade how extreme the text was that was being shared online.
Mm-hmm. Wow,
And
that's a really cool application.
yeah, a lot of fun. It was a very stressful time, but because it was being balanced with some other priorities. I didn't know until the end that I was supposed to be billing it full time, and I was billing it at 50% and carrying another full-time project.
Oh man.
Yeah, so and then eventually I moved from doing that to doing 4 things at once, and that's about when I melted down. But the other project was phenomenal, and I had I can't really talk about it, but I had some life-changing experiences that were really good, really incredible, positive experiences. Met some really talented people, visited some really cool facilities, and learned a lot, grew a lot as a person. I wish I had continued that path, but there were, I don't know. At the end of the day, it just it sort of fizzled. My time there came to a close.
Mm-hmm. Yeah, those projects sound super neat. And also, like, as we talk about concepts in a few minutes, like clustering and stuff, I would love to hear how like what we're doing compares to what you did, because I think there will be a lot of similarities.
Cool. Yeah,
Awesome.
I mean, I think most of the clustering was just super basic stuff. I don't even know if we ended up using it. It was for, I think that project is public. Yeah. So we did a project for Homeland on looking at my end of it was looking at the chemicals that would be most likely to be dangerous to a degree for use in a terrorist attack. But yeah, and so what I did was I used I don't think it made it into the final manuscript. I used so I can't say anything about it.
That's okay.
Yeah.
Yep, sometimes it's just like that, but in your head you'll be able to make the connections at least.
Yeah. But
Cool.
you really lucked out. I'm sure you worked really hard, but you found the right spot at the right time. This is an incredible field to have a good skill set in.
Yeah, I love it. Dawson, how do you feel about like analytics and like career prospects there, and like what kinds of things are you wanting to explore in analytics?
Well, all this just started for me. I worked for Enterprise Rent-A-Car for the past 14 years. And in my everyday life, I kind of use data to make decisions. Like literally for the past 4 years, that's what I've been doing. And I've been trying to get into data more at Enterprise, but it was so complicated. So I decided I was going to leave and just try it out. It just was amazing for me when I figured out how I could use data to make my job so much easier. And that kind of intrigued me a little bit. So I just started to explore it more and more and more, and wish I knew some of the stuff that I learned when I was at my job. But I'm kind of intrigued by figuring stuff out. Like my background, my degree is in telecommunications engineering. I just happened to get I just happened to work at enterprise because when I got out of school, it was 2008 and the economy was all crazy. So I just took a job and I was very successful at it. So I just continued, but just eventually I just wanted more. I just wanted something that kept me busy, kept my mind churning, and that wasn't it. And so now, this keeps my mind churning. Like it's continuous learning, but I love it because every day I learn something new, and I get the aha moment when I get to figure something out after I've struggled for a day or two, and then I figure it out. That makes me feel real good. So
I know, it's the best feeling. Cool, cool, awesome. Yeah, it sounds like both of you are like very well cut out for analytics and data science and these kinds of things, and your interest level is great. And yeah, this is going to be super fun. I'm going to share my screen. Let's see. Oh, it's on my other monitor. My bad. Okay. Are you guys able to see my code?
Yes.
Okay, perfect. And I also have my bank customer churn prediction.csv and my USA housing.csv files here, and you should too. If you don't, in the second block of code, you'll get the error, so we'll figure it out really fast. Okay, before we get into the code, I just want to kind of explain some of these algorithms in my PowerPoint, but I promise we'll get into the code super quick. So here's kind of like a little diagram that I threw together, which talks about the algorithms, or it just kind of classifies the algorithms that we are going to talk about today. So we have supervised and unsupervised learning. You'll recall we have the third category of reinforcement learning, but we're not going to do any of those algorithms today, so I just didn't include that here so it doesn't get all clouded up. So first, we're going to talk about some supervised learning algorithms. So we'll start with regression, where we will talk about linear regression, like I think Dawson mentioned earlier. So that's the regression algorithm we're going to do, but of course there are many more. And then in supervised learning, we are going to also talk about classification. So these are the two main types of supervised learning that are most commonly used. And in classification, we are going to talk about logistic regression. And we're also going to talk about why logistic regression isn't considered regression, because I know based on its name, that is super weird. And it took me a long time to realize that no, logistic regression is not a type of regression. So we'll talk about all that, so no worries. And then we will move over to unsupervised learning, and we'll do a couple clustering examples, both with the k-means algorithm. And we'll talk about why it's called that and all of that. But it's the most common, I think, unsupervised learning method. And so I wanted to do this algorithm because it's super powerful and also really fun to see. So let's start with, like I mentioned, the supervised learning. So just a little recap of what we talked about before the break, because I know it's been like half an hour now, and it's easy to forget things when we just learn them. So when we make a model using supervised learning, the first thing we're going to do in our code is we're going to first get our data into Python. So it's going to be our labeled data, and we have the labels. And then we are going to train our model with the training set. Here's a little diagram of the training and testing data that I made for you all. So this whole bar is the available data. And then we split all of our available data into a training set, which is usually like 70% of the available data, and then the testing set, which is usually 30% of the available data. But again, the way that we split that, I mean, it depends on people's preferences and maybe the type of data and things like that. But usually 70% and 30% is a good way to split it. So we split that data. We train our model with the training set. And then we can use that to make predictions on our testing set. And we're going to do this in Python in just a second. So we use our testing data to make predictions. And because our testing data is part of this original labeled data, we know whether it predicted correctly. So if we put in like a square, and of course we're not going to be talking about squares and triangles, this is just kind of an example. But if our test data contains a square, and it predicts that it's a square, we can say that that predicted correctly. And then we can come up with a sort of accuracy rate score to show how accurate our model is. So that's kind of how it works. So first, we're going to be talking about, like I said, regression. So what is regression? You might be familiar from it or familiar with it if you've taken a math or stats class recently, or just like heard about it. But regression is a technique for predicting a continuous outcome variable based on one or more predictor variables. And I tried to keep the math talk out of this as much as possible because I know for some of us it's been a while since we've taken a math class. But do either of you know what I mean when I say continuous outcome variable, or do I need to explain that? I will take the silence as I need to explain it. Okay, so a continuous outcome variable just means that, okay, so the outcome variable is like the dependent or Y variable. It's the one that we're trying to predict. And in machine learning, it's often called the target variable. So that's the one that we're trying to predict. So if you think about it on like an X and Y axis, that's the Y axis. Continuous outcome variable just means that that dependent or target or y-axis variable needs to be a continuous numeric variable. So it's going to be a number that can be like any number, like temperature or like price or something like that. It can't be something like a category. So it couldn't be like car type. Like that is not a continuous outcome variable because car type would be like SUV, sedan, convertible, things like that, where like that's not like continuous. It couldn't be any value. So we can only use regression if we are trying to predict a continuous outcome or dependent variable like price or temperature or something like that. And we can do it based on one predictor variable. So like if you think back maybe to like when you took algebra for the first time, which might be a lot to ask. I know I have a hard time remembering that, but we did things like y equals mx plus b, where we would try and predict, say, someone's grade in a class using the number of hours they studied. So our predictor variable would be the number of hours studied, and the continuous outcome variable would be the grade in the class, because you can get any grade in a class ranging from 0 to 100. So that's an example of when we would use one predictor variable. And so that's just a simple regression. But we can also do a multivariate regression, which means we have multiple predictor variables. And this is really where it becomes a lot more useful. So when we have multiple predictor variables, we can start making predictions about, let's say, the grade in the class by a lot of different things. We could do the number of hours studied, the number of classes somebody is taking, their major, because somebody's college major might predict how well they do in a certain class, maybe the professor, things like that. So we can use a lot of different factors in order to make predictions with regression. And a lot of times having more predictors can be helpful. But we do want to be careful because sometimes when we have so many predictors that our model is super good at predicting on the data we already have, there's a concept called overfitting, which refers to when our model is so good at predicting to our training and testing data that it's overfit to that data. And then when we apply new data that might be different and have different trends, it's so good at predicting the original data that it's not as good as applying it to the new data. And so it's always kind of a balance of figuring out how many predictor variables we really want. And that's a very common kind of conundrum in supervised learning, especially, is figuring out the balance in having the right number of variables to where our model is good at predicting to our training and testing data, but it's still applicable to new data in the real world. So let's look at some examples. One of the most common examples is like predicting this continuous outcome variable of annual income with factors like years of schooling, hours worked per week, and sector. We could also try and predict life expectancy with factors like weekly exercise, gender, blood pressure, diet, things like that. So as you can see, the most important thing to get here is that we're predicting like a number variable, a numeric variable like annual income, life expectancy, housing prices, things like that, instead of categories with regression. So in the algorithm in Python, we're going to talk about linear regression, which is the most common kind of regression algorithm, which essentially just assumes that there is a linear relationship between all of those predictor variables, which you can think of as X, and the outcome variable, which you can think of as Y. And so we use our training data to create a line of best fit. So you can see here, you can assume these blue dots here are our training data. And if we were to say, what's the best line that we can make to fit all of these points? And there's a mathematical way to come up with this line, but Python's going to do it for us, thankfully. And so it's going to come up with this red line right here. That's our line of best fit, which best summarizes our data. And so if we were to put a new point onto that data, this line would give the best prediction of where it would be. So we make that line, and then we use that line on new data. So if we have like new data that we want to predict where it goes, we can kind of put it on this line, and it'll make a pretty good guess. And so as you can see, this would be our outcome variable, and then our predictor variables can be represented on the x-axis there. But of course, when we have multiple predictor variables or multiple x's, it becomes multidimensional because we have more than just two variables, which are represented on this 2D graph. Any questions on the concept of linear regression before we do some code?
No, ma'am.
Awesome. Okay, let's switch into the code then. So I'm going into my workshop code.ipynb, and we're going to start in this linear regression section. And I put some notes in here so that you can look at these and reference them later. And I just want you to remember that linear regression is supervised learning, and it's in the regression category. So I just put that there for you. So I'm thinking since we already have the code, it's probably easiest if we just kind of run it together and talk about what it's doing instead of spending the time trying to like get all of this code down. Because I think the most important part, you'll see most of the code isn't like very, very complicated for the most part. Some of it is a little complicated. But I think the important thing here, rather than focusing on the code itself, is focusing on what it's doing, especially when it's talking about machine learning. Because I think a lot of people know how to run this code, but few people know what it really means, and that's the important part. So the first thing we're going to do, of course, is import our required libraries because we need a lot of things to be able to run this. So let's just run this first cell together to import our required libraries. And then just like unmute and let me know when you get those imported.
Done.
I'm good.
Awesome. Okay, so now we are going to read in our data. So the way we're going to read in our data, we're using pandas. So you'll see I have this line up here that says import pandas as PD. I have both of you used pandas before?
I have.
Okay, Matt, have you used it?
Yep.
Okay, awesome. Then I won't get into what pandas is if we've all used it. But so you've already used this. But we're just going to read the CSV using the pandas.read CSV method. And the path here that I put, so the place that I told you to upload these files, this path should work for you. And if you're not familiar with Google Colab, the way I got that path was I just like right clicked on my file and I said copy path, and then you can like paste the path. So if you're having any issues with running this, try copying and pasting the path of wherever you uploaded it into that read CSV method, and maybe it'll work better. But I am just going to run this really quickly. And then I've called it housing data so that we can distinguish the different data sets we have in here. And I used the head method. And I used the head method because it just returns the first 5 rows of my data frame. So are we all at this point where we can see our entire table?
Yes.
Okay, cool. So as you can see, we have some housing data. It's very surprising considering our data set is called USA Housing. So it looks like we have some variables like average area income, average area house age, average area number of rooms, average area number of bedrooms, the population of the area the house is in, the house's price, and the address. So what we want to do here with our regression is we want to predict the price of a house because that's our numeric variable, our numeric continuous variable that we are interested in predicting. based on all of these features, the area, income, house age, number of rooms, number of bedrooms. Do you think we're going to use address?
No.
No. And why aren't we going to use, why are we not going to use address?
It'd be really hard for the model to fit the relationship between address and price. It would need to know neighborhoods and all sorts of things.
Exactly, exactly. Because each individual house has its own address. And so there's not going to be like overlapping addresses. And if they are, that's going to be wrong and confusing probably. And that's not going to be helpful for our model in predicting the price. What we could do is we could extract, for example, the state or the zip code or the city or things like that from this address column, and we could use that.
GPS coordinates might be interesting.
GPS coordinates like longitude and latitude or something like that. That could be more helpful. Yeah, so we could do things like that, but just this plain old address column is just not very helpful. Especially in the way that it's formatted. We would have to do some substantial cleaning and extraction to be able to use it. For simplicity, because this is pretty good data, we actually are not going to use address, but I just wanted to talk about what we could do if we had more time and if we wanted to include some geographic information. We could do, for example, like zip code or city or longitude, latitude. One thing I do want to point out, it's possible that there might be some sort of correlation between like zip code and area population. So it's possible that area population might already kind of help us get the information that we would be wanting from like zip code, for example. But we would have to do a little bit more analysis on that. So yeah, I think area population is going to be pretty helpful for us in terms of price, because area population can show whether you're in like an urban area or not. Okay. And then here I just put a little note for you that price is the continuous numeric variable, and that's how we know that this is a linear regression problem. So let's work on our model. Step one is we want to define our predictor and our outcome variables. So usually in machine learning, in Python, we talk about our predictor variables as being a capital X and our outcome variables as being a lowercase y. You don't have to do it this way, but most, like when you see other people's code, probably you'll see the predictor variables as an uppercase X and the outcome variables as a lowercase y. So here what we're doing is we are saying we want our predictor variables, or X, to come from our housing data frame, and we want these columns. We want this list of columns. We want average area income, average area house age, number of rooms, number of bedrooms, and area population. And we want, for our Y value, our outcome variable, we want price. So if I run this, and mine ran very quickly because it's a pretty easy computation, let's run x.head. So x.head will give us the first 5 rows of X. And as you can see, this is the entire housing data frame. It just doesn't include price because these are our predictors. Can someone tell me why we wanted to remove price from our predictor variables?
Because price is our outcome variable.
Exactly. Price is our outcome variable. And so while it would make our model on our training data really, really good if we included price here, when we have new data coming in that we want to apply this model to, the whole point is that we don't know the price. So like Matt said, like it's our target variable. So even though we have labeled data, so labeled data means that we have the price here, we can't include it in our predictor variables because when we get new data to make predictions with our model, we're not going to have the price. That's what we'll need to know. So I just wanted to make sure that was clear because it's surprising the number of people who get to this point and are a little confused on that. So I just wanted to make sure we were clear on that. Okay, so we have all of these. Oh, did you have a comment?
Oh yeah, I was just gonna joke about these are some nice houses.
Yeah,
At least
for
the
real.
first 5, right?
Yeah, for real, for real.
Should be so lucky. Anyway, sorry for derailing.
Honestly, that's great, and that's a great point because I hadn't even like looked at the data closely enough to make that observation, which is like bad data analyst, Melanie. Like that's bad. I should really like look at the data better. So that's a good point. It's always good to take a look at the data that we're looking at and make some observations before we get started. Yeah, these are nice houses. Okay, so yeah, let's do y dot head. Another way that we could do this, does anyone know another way that we could look at the first 5 rows? Like using pandas?
Isn't there like a top method?
Oh, I actually think there is. That wasn't what I was. Let
That
me
might
look that
not
up
be
really quick.
accurate. I think head is the correct way to go, but well, you could index it, right, and do 0 to 9 or something, right?
Right, right. So we could do.
Isn't there like a first 5 row, a print first 5 rows command?
So I was thinking indexing. We could do some sort of for loop or something like that to get the first 5 rows, like you were saying. But I was just thinking some indexing like this. That was just a little pandas note, not important at all. Just because you guys know pandas, I think we can have some fun. Okay, so the next step is let's split our data into our training and our testing set. So to do that, we need another library or part of the library to import. So we're going to be importing train test split from sklearn model selection. So you're going to really use this in most, if not all, supervised learning methods. We always have to import this. And then what we're saying is we want to define our training set for our X predictors, our testing set for the predictors, the training set for the outcomes, and the testing set for the outcomes. Because we've already split our data into the predictors and the targets. And so that's why we have to do the train and test for both of those because they're already split. And this method knows how to do that. So it's just going to split it, our X and our Y for us. And here we're saying we want our testing data to be 30% or 0.3 of the total data. We have this random state here because it's going to shuffle up our data because sometimes the data is ordered. And so like if it's ordered in terms of like price in ascending order, if we split just at like one point, all of the less expensive houses would be in the training set and all of the most expensive houses would be in the testing set. And so that's not going to be the best for building a model. So when we're doing random state, we're just going to shuffle up our data. If we have the same random state, we'll have the same shuffle. So let's just all do random state of 42 so we get the same model, but you can put whatever you want. But that's just because we want to mix up our data before we do that split so that it's a bit more random. So let's run this. And then the third step is we just want to prepare our data for regression. And so we're just going to do a little bit of data transformation. We're just going to do some scaling, things like that. I won't get into this too much because you can take a whole class on this. It can get very complicated, but let's just run this to prepare our data for regression. And then this is the important part, step 4. So when we run, and by the way, is anyone having any like errors in their code or are we all good here?
I'm good, thanks.
Awesome. Okay, so let's run step 4. With step 4, so what I've done here, this is important. You need to import the linear regression model from sklearn linear model. So I've imported linear regression. And then I want to call mine linreg. A lot of people will also just call it model. I'm just going to keep mine as linreg because we have several models in this file. And while it's okay, and as we know when we do Python, we can use the same variable and replace the value. I think it's better when we can to just have different variable names for our different models. So a lot of people would just call this model. I'm going to call it linreg. And I'm going to say that I want to use the linear regression. This is the line of code. And I'm going to put this comment here, and I would encourage you to do it too. this is the code that creates the model. It's this linreg.fit. So it's this .fit method that creates the model. And that's the case with most models that we're going to be using with sklearn. And by the way, if there's parts that don't make sense, feel free to ask. Because I know we probably have varying knowledge levels of Python, and I don't know exactly where you're at in Python. So if there's parts that are confusing, let me know. But what we're going to do is we're going to fit this model using our training data. So let's go back to here. So we use, actually, no, I think there's a better picture. Maybe this one. So we use our training data to train the model, which is to create the model. And then we're going to use our testing data to evaluate the model. So we're creating our model using our training data here. And then once we do that, we'll get our linear equation, which best represents our data. And that's going to be represented in terms of a y-intercept and then a bunch of coefficients for each of these variables. So I put, just in case you're not familiar with the linear equation, I put, let's see, I put it here. So essentially we have y, so our predictor, so we're going to say price equals this intercept, which is where it'll start on the y-axis. So the intercept, which looks like is this number right here. And I got that number by saying linreg, which is our linear regression that we've created using the fit method, .intercept. And we have an underscore after intercept. That's how we obtain the y-intercept. So that's that part of the equation. And then each of these x's, so x1, x2, x3, ... all the way to however many x's we have, those are the predictors. So our predictors are average area income, average area house age, num rooms, num bedrooms, and population. So those are our different x's. So we have x1, x2, x3, x4, x5. And then all of those little like betas in front of those x's, that's what these coefficients are. So essentially our linear equation is, wow, that's a big number with no commas. Let me read it. It's so tiny. It looks like 1,228,219 plus, and then 232,697 times average area income, and then this coefficient times average area house age, etc. And that's our model. So we just plug these numbers we've been given here, and this is our model. Does that make sense? Are there any questions on this equation?
No, those are some nice houses.
Mhm.
Yeah, for real. For real. So yeah, we just plug in then. So if we're given a new house, we start with this intercept, and let's say the average area income is like 80,000. We would say 80,000 times, and then this. And then average area house age times this. And sometimes we have negative coefficients. Here we don't seem to, because these are crazy houses. Yeah, so what I've done here is I printed the intercept, and then I've printed our coefficients from the linreg coefficient, and then I've placed them next to in this list, because I've just made a data frame essentially to organize this information, because I wanted you to be able to see the coefficients themselves next to the columns. So that's why I organized it like this, if you were wondering what this line did right here. And then I printed it. Any questions on step 4?
Looks good.
Awesome, awesome. So now what we want to do is we want to see how accurate is the model on our training data. And then after we do that, we can evaluate it on the testing data. So what I am going to do is I am going to use the training data to predict what the price would be. So with the training data, we ignore the fact that we already have labeled data. So we basically are just using our predictors. We don't have the price, even though we do. We're just kind of ignoring it. And we're predicting with our linear model what the price is for our training data would be. And we store that in training predictions. And then we use this right here in order to make an accuracy score. So we're saying how accurate were those predictions, because we have the price for that training data. And so we're able to see, okay, it was actually right like 92% of the time. That's great. But that's on our training data, and we built the model using the training data. So we expect it to be pretty high. If it wasn't, it would just be a bad model. We use a score. It's called the R-square score. So it's called the R-squared score, which is basically, if you've heard of like the correlation as being R, it's the correlation squared. And what it represents is like what % of the variation in our dependent variable, which is price, can be explained by our model. So we could say here that like roughly 92% of the variation in housing price can be explained by our model, and that's pretty good. So that's just a quick check we did on our training data to make sure our model is somewhere in the ballpark. And then what we need to do is we need to go to our final step, and let me show you. Oh goodness, where did it go? Oh, I think it was all the way up here actually. Yeah, so then we're going to apply our test data to validate our model. So what we're doing is the exact same thing we did with the training data, but this is the important one. So I'm going to say this is the important part of the evaluation, if you want to add that. And so we then have our test data, which is the data that we had kind of taken out. We didn't use it to create the model, but it's still part of our original data set. And that's why we use it to test. So then we say, what is the accuracy score or the R-squared score of the testing data? And we run this and we get 91.4%. So that means we can say approximately 91.46% of the variability in housing prices is explained by our regression model. That's pretty good. Another thing to note is that the accuracy score of the training set and the accuracy score of the testing set is very, very close. And that's good. That's what we want. Usually the difference will be a little bit bigger. I think this is just like good data. Usually our data won't be this good. And so usually the drop off will be a little bit bigger. But when we have a really big difference between our training accuracy and our testing accuracy, that's a sign that there's something a little bit wrong with our model. And that's the concept I was referring to earlier called overfitting, which means we've overfit to our training data. And now it's so highly specialized to predict to our training data that it's not doing a good job predicting new data. But we can see that our model is not a victim of this because these two accuracy scores are very similar. Does that make sense?
Yes, ma'am.
Okay, great. Any questions on linear regression before we move on? Okay, back to the slides. So now, that was, okay, yeah, that was our regression. And I can give you these slides at the end if you want. I just put the steps here so that we can see them outside of the code too. So the second one we're going to talk about is classification. Let me go back into the slides actually. So now we're still in supervised learning, but we are in classification. So classification, oh my gosh, very big typo. Sorry about that. Okay, classification is a technique for predicting a discrete class variable based on one or more predictor variables. And so it's very similar to regression because we're still predicting a variable based on one or more predictor variables, and we do a pretty similar process. But the difference is here we have a discrete class variable instead of a continuous variable. So what that means is we have categories. So we could have weather type. We could be predicting whether the weather is going to be like a thunderstorm or sunny or cloudy or rainy, because those are discrete class. Well, I guess thunderstorm and rainy is not really discrete, but let's say thunderstorm or sunny or cloudy. Those could be the three categories. Or we could have car type. Or we could have, we're predicting someone's favorite color and there's different categories. So that's what I mean. It's not a number, it's just like a category. And so that's what we use classification for. One of the most common types of classification is logistic regression. And we're going to talk about that on the next slide because that's actually the algorithm we're going to use. But just some examples of classification. We could predict what genre a song is based on its tempo, its pitch, its rhythm, and its spectral properties. So we could get like a database of songs, pull all of their tempos, their pitches, their rhythms, a bunch of their properties into like a spreadsheet, put that into Python, and we could make predictions about that song's genre. Another thing we could do, and this would probably be logistic regression if I had to guess, but we could predict whether an email we received is spam or not. And this is what like Gmail does or whatever email tool you use. It's using a bunch of factors like what's in the subject line, what kind of email address is that email from, and it uses those features in order to predict whether that email is spam or not. And if it's spam, if it predicts that it's likely spam, it will put it in your spam folder. And if it predicts that it's fine, it's a good email, it'll go into your main inbox. I don't know if it's happened to you. It probably has, but these are not always correct because it's a model. It's a prediction. I've had very important emails go into my spam folder before, and I've certainly had spam go into my inbox because sometimes the accuracy isn't as high as we would want it to be. But that's because it's a model and it's a prediction, and so the accuracy is not always going to be 100%. So the algorithm that we are going to use is logistic regression. Another one, a common one would be like a decision tree, for example. But this is one of the most common ones, and it's logistic regression. And we're going to use it because I think it's really important to understand the concept of logistic regression, because a lot of people will erroneously categorize this as a regression technique when really it's classification. I don't know why it's called regression. It probably shouldn't be. It's a little bit misleading, but it is classification. And so the important thing about logistic regression is we can only use it when our outcome variable has two options, which also is referred to as binary. So it's a binary outcome variable. So for example, whether a borrower will default on a loan, yes or no, 0 or 1. Whether a purchase is fraudulent or not, 0 or 1. Whether a patient has a disease, 0 or 1. Now, this disease one could be a little more complicated because maybe we want to classify what type of disease it is. And if we do that, we would have to use a different classification technique because logistic regression only applies if the outcome variable has two options. And so usually no will be represented with 0 and yes will be represented with 1. So here, instead of representing our data with a line like we did in linear regression, we represent it with a logistic function. This is called a sigmoid function, and we won't get into the math because I think just keeping it a little more conceptual for now is fine. But as you can see, there's kind of this little S, and this is what kind of categorizes the logistic regression and that logistic function. So what we do is we are using our training data and testing data, I guess really our training data, to transform our outcomes into values between 0 and 1. So as you can see here on this, and actually let me make this a little bigger so you can see it better. So we have 0 all the way up to 1. So it just transforms all of our data points into having outcomes from 0 to 1, where 0 represents no and 1 represents yes, usually. Like at least it represents these binary options, and usually like the no option will be 0 and the yes option will be 1, just as like a coding preference. And so as you might be able to guess, these outcome variables, the new transformed ones, represent probabilities because we're going from 0 to 1, and that's the range of probabilities. And so what it represents is the probability that this point actually belongs to this upper class, so the yes class. So let's say that this regression, this logistic regression, represents whether a purchase is fraudulent or not. So the points down here are the points that are less likely to be a fraudulent purchase. Sorry, let me get some water. Oof, I've been talking for a while. Okay, and then the points up here represent the purchases that are more likely to be fraudulent. And we know that because the probabilities closer to being 1 are the probabilities that are more likely to be fraudulent, because we've decided that our fraudulent class is going to be the 1. And so usually we'll define some sort of threshold, and all of the points below that threshold, usually it's like 0.5 because that's 50%. But depending on the type of problem, we can define it differently. And so the points below that threshold, we would predict would be no, and the points above that threshold, we would predict to be yes. Any questions on conceptually how this works?
I mean, I would.
Not really. I'm following along.
Okay, sounds good. What about you, Matt?
Oh, you totally lost me. If you could run that through one more time, that'd be great, please. I'm sorry I drifted off.
Okay, sounds good. And no worries, like, especially because there's only 2 of us, we have time to be able to go through these concepts again.
Okay.
So it's great that you let me know.
Let me be a little more specific then to make our communication more helpful. So you're going to take a number that could be any number. Oh no, because it's only a 0 and a 1 that's going in, right? The input is either a 0 or a 1 to begin with.
Okay, so let's say, yeah, I think I see maybe where we're getting kind of mismatched. So yeah, we're predicting whether a purchase is fraudulent or not. And so that's going to be either 0 or 1 because we know. So let's say it's not fraudulent. We define all of those as zeros. And then we have ones that are fraudulent, and we define those as 1s. And so then we kind of take that outcome variable off, like we split into x and y, and we use our x's to predict whether that point will be in 0 or 1. But we predict using a probability. And so these are the predictions, the probabilities, anywhere from 0 to 1. And that's how we come up with where the points fall on this axis here. Does that make more sense?
Yeah, I think it'll become more clear as we work it. Thank you.
Okay, awesome. And even later we can come back and like try and talk about it again, because I know this one is a little bit more confusing. Because we're not trying to predict like a number, we're trying to predict options of a binary outcome. Okay, I'll move on for now, but if we find it still confusing, we absolutely have time to stop and talk about it later. So let's look through an example, because I think sometimes the best way to make things clear is to just do it with an example and see how it works. So we are going to be using customer churn data. Do either of you know what churn data is? So churn data is like,
retention.
Oh, go ahead.
Like retention, customer retention.
Exactly, customer retention. So it's like, are we going to lose this customer? Mm-hmm. Exactly. So we are going to follow very similar steps. First, we are going to define our prediction and our outcome variables, just like we did before. Then we're just going to make sure our data is in the right format. We'll split into training and testing sets. We'll create our logistic model. From the model, we'll get our intercept and coefficients. And finally, we will evaluate using our testing set. So let's go back into the code. And let's move to number 2, logistic regression. So this is supervised learning and classification. So I'm going to read in my data. So I'm reading in my data. Do you all get this data frame correctly when you read in the data and run the head method?
Mine came out good.
It works?
Yes, ma'am.
Okay, awesome. What about you, Matt? Okay, maybe Matt is muted or had to step away. but feel free to stop me if we run into issues. So this data here is predicting whether a bank lost its customers, or it's showing whether the bank lost its customers. So this is historical data. It's already happened. So 1 means that customer left. 0 means that customer has not left. Yeah, it's customer retention. And it's for a bank. And so we have all of these characteristics that we're going to use to predict whether that customer left or did not leave. And as you can imagine, this is pretty important for companies because we want to retain as many of our customers as we can. And if we can see what characteristics would make a customer most likely to leave our company, we probably want to target those customers very specifically in order to keep them. So we have, and keep in mind, this is for a bank. So that's why we have some of these variables. So we have their credit score, the country they're from, the gender, age, the tenure, which is just the number of years they've been with the company, their bank balance, the number of products they buy from the bank, the number of, actually, this is only ones and zeros. So I think this is whether they have a credit card or not, yes or no. We have whether they're active members, we have their estimated salary, and finally, we have the outcome variable, which is the churn. So let's build a model to predict whether customers will leave the bank. So 0 is they will not leave, 1 is they will leave. And so that because that's only 2 categories, that's a logistic regression problem. So step 1 is to define the predictor variables and the outcome variable. So let's say X equals, and we have our churn data frame, and then we have all of these categories, which we're going to use as our predictors. And then churn will be our Y, because that's what we want to predict. So we've split it up. And let's take a look at X. So we can see it's everything except for churn. And Y is churn. Are we all good?
Yeah.
You know?
Okay. Oh, Matt, did you have a problem?
Yeah, no, I had to connect. I ran out of power, so I had to connect to a different workstation and the microphone wasn't working. I'm sorry about that.
Oh, no worries. Were you able to get the collab file back open?
Yeah, so the collab file is open. We're on x.head, y equals churn data, subset churn, x.head. We are. Yeah, it runs fine. Thank you very much for your patience.
Okay, great. Amazing. So now let's do step 2. So this one we didn't have to do with the linear regression, but we do have to do just because of the way that the linear regression function that we're going to use, which is this down here, works. Because of the way, and different ones will kind of work differently, but the one that we're using requires that we convert our categorical predictor variables to be numbers. So what that means is, because maybe, I think categorical is maybe jargon, so let me try and not use that. We have some variables in our X, which are not numbers, like country and gender. When we're using our model, we need these to be numbers, at least for the specific logistic regression that we are going to run. So we just need to kind of format these to be numbers. So there's 3 options for country, and let me just show you that. I'm going to make a new cell. And I'm going to say churn data. The column is country. Are you all familiar with the value counts method?
Of course, I don't think I've used that before.
Okay, it's super helpful. So let me show you how it works. Basically, when we run this, we get the count for each of the categories inside of this column. So it's similar to using a group by and making the aggregate function count. This is just like an easier way to do it. So this means in the country column, we have about 5,000 people from France, 2,500 from Germany, and about 2,500 from Spain. And so we can see that there are 3 categories. So we'll expect when we change these to numbers, we'll have like 0, 1, and 2 probably. And let's do the same with gender just to make sure. But let's see what the classifiers are for gender. Okay, so in this data set, it's just male and female. And so we'll expect for country, we'll have 3 categories, and for gender, we'll have 2. So I'm just going to say, let's look at the non-numeric variables, just if you want to add that to your code. So yeah, the value counts method is part of pandas, and it's really great because it allows us to see the counts of the different categories of variables. So now what we're going to do is we're just going to convert these two to be numbers, because we just need to do this to make our logistic regression model work. And the way we do this is using the label encoder. And so it's another part of this sklearn library. So it's part of the pre-processing because we're pre-processing our data. So we just import pre-processing. I'm just going to call my label encoder LE, so I don't have to type out pre-processing.label encoder like every time. So all we have to do is just say we want to like run the label encoder. You'll remember the fit just means we're going to run that model. So we're going to run it on the country column of X. And then we want to run the transform method of label encoder. So we're just going to transform this to be numbers. And then we'll do the same for gender. So now when we run x.head to see a preview of our predictor variables, you'll see our country is now 0. And let's actually just look at this. Let's say X country, and let's do a value counts again. Now we can see, instead of like we had before, and let me comment this second line of the above cell out so we can compare. So we had France, 5,014. Now France is turned into 0. Germany is turned into 1. Spain is turned into 2. And there are multiple ways that you can do this, as you can imagine. This is just the way that I do it. So I'll uncomment that line now. I can get rid of this value counts because we don't need it for our model. This also isn't necessary for the model. It was just to kind of demonstrate that to you. But step 2 is, so now we have our countries coded as numbers and the genders coded as numbers, which isn't like changing their value. It's just putting them into categories that are numbers to run our model. Any questions on why we did that or how we did that? Okay. So now what we're going to do is, like always, we're going to split the data into a training and a testing set. We're doing it in basically the exact same way. My random state is 105. If you want a different model than mine, you can do it differently. And again, I say I want the test size to be 0.3 because I want 70% of my data to be training and 30% to be testing. So I will run this. And now let's build the model. So here, last time you'll recall, I imported linear regression. This time I imported logistic regression, and I'm going to call it log reg. So I have my logistic regression function, and this is the line, again, I put this on the last one, but this is the line that creates the model with the training data, because we use the training data to make our model. So I have logreg.fit that creates our model. We create our model using our training data. And so now we can get the intercept after we've created the model, as well as the coefficients, just like we did with the linear model. It's just that now, instead of having in our model, instead of having a straight line like this, our outcomes look like this. So our coefficients will make a curve that looks like this, where all of the points down here are going to be classified as 0, which means they won't leave, and all of the points up here being close to 1 or above 0.5, that means that we predict that they will leave. And so the customers that are on this upper part of this curve, so this data, these intercepts and coefficients, create a curve which looks like this S. So the customers up here in the top right corner of that graph are the ones that we want to target because we don't want them to leave. Matt, is that part making a little bit more sense now, or is there a part we can go deeper into to clarify?
Could you explain that again for me?
So here, we ran our model. We ran our logistic regression model with our training data.
Okay.
And from that, we get an intercept and coefficients. And we get an intercept and coefficients, which create a line like this, or like a curve, like an S curve.
Okay.
Before, you'll recall, we had an intercept and coefficients that created a straight line. Or technically, when we have, okay, I need to go into presentation mode, I think, so I can draw. So technically, when we did regression with multiple X variables, it'll look kind of more like this, but it'll be kind of like going up like that with those points.
Okay.
With our logistic model, now our coefficients and intercept, so our intercept will help start it, and then our coefficients will make a line that looks, well, I'm doing a very bad job at tracing this line, but it'll look like this. So it'll look like an S, like this. And so our 0.5 is right here. This is a 0.5. So up here, one represents lose customer. So I'll say lose. 0 represents keep in terms of customer retention. And I'm drawing this on my little like keypad on my laptop, so I apologize. So we have lose and we have keep. And that's a 0.5 probability. 0.5. So we have this imaginary line here. So if the points are up here on this line that are represented by the coefficients and intercept that we got from our model, so if the points are up here, that means that there is a greater than 50% chance that we are going to lose those customers. But if the point is below that line, that means there's less than a 50% chance that we are going to lose those customers, which means we are more likely to keep them. So these are the at-risk ones. These are the at-risk customers that we would want to target if we were doing some sort of like marketing campaign. And these are the ones that are probably okay. Does that make a little bit more sense?
Yes, absolutely. Yes.
Awesome, awesome, great. I know, like, looking at the curves and the lines, and it can be like very confusing. But if we think about it in terms of like we lose these ones, we keep these ones, I think it can be a little bit easier. Another thing I wanted to call out is this 0.5 is somewhat arbitrary. Let's say it's like really, really bad if we lose a customer, and it's like we don't care if we keep them. We might want to lower the threshold. That is not a straight line, sorry. I don't know how to erase it, but like we might want to lower the threshold if it's super, super bad if we lose. So for example, in like contexts like health or something like that, instead of like money, it might be more important. So we might want to lower that threshold if that's the case, if it's really, really bad if we lose, because we want to minimize the predictions that we would get wrong in that way. So I just put this 0.5 here because it's kind of like an arbitrary one that we commonly use, but we can change the threshold if we want to. And always the ones that will be above the line will correspond with this category, and below the line will correspond with this category. Okay, how are you feeling about this now, Matt? Is there another part I can explain for you?
No, I get it. I think so. The coefficients, the coefficients define the location along the sigmoidal curve of the independent. Oh,
exactly.
Yeah, define the location along the sigmoidal curve. Understood.
Exactly, exactly. So I will discard my annotations because they look awful. So we plug in any given point that we have into this equation right here, which I know it doesn't look like an equation, but it's an intercept and coefficient form. And then we use them to put them on this line. So any given point can be on this line. And then depending on its location on the line, we predict whether it's in the 0 class or the 1 class. Awesome. You guys are killing it. Yeah, this is a hard concept, and I feel like you're getting it pretty quickly. So, okay, now what we're gonna do is, and feel free to ask me later to come back to this, because repetition is key in learning things. So now we are going to do exactly what we did with our linear regression and figure out how accurate our model is using the training data. So when we run this cell, I get 78.6%. That's pretty good still. Not as good as the linear one for the other data, but this data might be a bit more complicated. But more importantly, we need to evaluate the testing data. Because that's the data we didn't use to create the model. It's other data, so it's more important what the testing data accuracy looks like. We actually get a higher number for this. And that is a red flag. That's weird. It's weird that with other data that we didn't even use to create our model, we got a higher accuracy score. That is just very strange. And so when we see something like that, we think, okay, maybe we underfit our model. So I'm going to put another comment. Maybe this is underfitting. Because the accuracy of the test set is higher than the accuracy of the training set. That's just very strange, and it doesn't happen very often. So what that means is we might want to go back and redo our model. Let's see if we have more categories in the data that maybe we weren't given initially. Maybe we want to weight different categories like that are more important differently, things like that. Because it is a little bit strange that our testing accuracy is higher than our training accuracy. Granted, it's not that different. It's like basically 78.6% versus 79.6%, so it's 1% different. But I just want to like kind of train you all to, when you see a testing accuracy that's higher than the training accuracy, start asking some questions. Okay. Any questions on logistic regression?
No, good. Explained good.
Okay. Okay, so we can move on to clustering. I wanted to see, are you all like good and fresh, or do you want to take like a 5-minute break before we move on to the next algorithm?
We could take a 5-minute break so I can grab some water.
Yeah, okay. I know it's a long time to sit at a computer. So let's take a 5-minute break. Let's meet back here at 50 after the hour, and we can get started with clustering. I just don't want to like throw so much code at you all at once. So I'll put it in the chat so we can remember. So let's meet back at 50 after the hour. So I will see you all back in 5 minutes. Okay, welcome back. We'll get started in just a second. All right. Is everyone back?
Yes, ma'am.
Amazing. What about you, Matt? Maybe Matt is still on break. We can wait until like 1:51 since I know I said 1:50. Okay. Let's talk about clustering. So, and let me go back into my slides. Okay, so now we're going to move on to unsupervised learning, and we're going to talk about clustering. Oh, wrong screen. Okay, so clustering is a technique for grouping similar data points together into clusters. so into groups based on their intrinsic characteristics or similarities. And so I think maybe the example we used for unsupervised learning before was fruits. And so we can use intrinsic characteristics like texture, like color, shape, size, things like that in order to group those fruits into clusters. And each cluster should ideally represent a different fruit type. So ideally, the data points within the same cluster are more similar to each other than those in other clusters. So what that means is we want all of the features of all of the apples to be more similar to the other apples than to the peaches. And that's what allows us to group different data points into clusters. So for example, one way we could apply this is if we wanted to do some customer segmentation. So if we wanted to group customers into different customer segments, which is kind of a business term, based on their characteristics. Another one, I know we've talked about this a little bit, if we want to identify anomalies or outliers in the data. So we could have a cluster that represents the normal data. And then if it's outside of that cluster, we know that it's an outlier or an anomaly. That's called anomaly detection, by the way. Oops. Okay, so our algorithm here is called k-means. This is the most popular unsupervised learning algorithm, at least right now. And so we use k-means when we have unlabeled data without defined categories or groups. So we just give it a big group of like pictures of fruit or something, and then we tell it to categorize those into groups. And so the only thing we really need to do with k-means is tell it the number of clusters. So we need to tell our algorithm how many clusters to group it into. And so here's like an example. You can see we have some data points here, and we can see, okay, it looks like we maybe want 3 clusters because it looks like there's kind of 3 distinct groups. So this would be a case where we might want 3 clusters. If we did 4 clusters, maybe it would group these 3 points right here separately from these right here. Or maybe, let me get my pen out, maybe it would make like this right here its own a separate cluster if we had 4 clusters. But here we're just saying k equals 3. 4 if I have that extra cluster in, but we don't want that. So actually, let me erase this. But here we have k equals 3. And k just represents the number of groups we want. So when we say k-means, we're saying, okay, that's the number of clusters we want. So here we have 3 clusters. So that would be k equals 3. Does that make sense? Okay.
Yep, that's great. Thank you. Sorry, I was away for some.
Mental analyzing sometimes. Yes, it does make sense.
Okay, awesome, awesome, and no worries.
I ran into this problem a while ago, and it'll take me a while to remember exactly where. But when it's unclear what the number of clusters ought to be, what methods do you recommend for determining the number of clusters? Isn't there some sort of V-plot or something, or?
Yeah, let me show you actually. That's a great question. Because yeah, it can sometimes be like a little bit hard to determine the appropriate number of clusters. So let me actually go into the code. You don't have to do this. I'm just gonna make some cells at the bottom just to, oops, that was the top. Just to kind of show you. So I'm going to call it determining the appropriate number of clusters. And maybe this is a good example. We're going to do an example of clustering with handwritten numbers, but let's just do an example where we just have some points. So I am going to just copy and paste some like import statements so I don't get errors. And then I'm going to do from sklearn.datasets import make blobs. And what this is going to do is it's going to make a scatter plot with a bunch of points on it. So I'm going to define my variables and I'm going to say x, y equals make blobs. Let's do like 400 points. And again, you don't have to follow along. I'm just going to kind of show you an example. We'll have 5 groups, random state equals 1. And then let's like show the scatter plot of that. So I think it's like scatter x And then I think this should give us our scatter. Okay, so don't worry about the code I used to get here. Let's just say we have this data right here. So we have this data. We can see visually that we probably want like 4 or 5 clusters, but how do we actually go about doing that? And like figuring out the appropriate number of clusters. So what we can do is first we can make our clustering model. And so let me just show you. So it's going to be from sklearn.cluster import k-means. And so before we were importing from regression, we were importing the other regression models. Here we're going to import k-means clustering. And I'm going to say model equals k-means. And then let's just first define our clusters to be 5. And then I'm going to do random state 1 because it doesn't matter what random state we use. Sorry, let's see. Oh, I spelled clusters wrong. Okay, and now let's do model.fit to create the model. And now, oh, what did I do wrong? Oh, sorry, sorry about that. We need to fit it to our points. Okay, now what we can do is we can plot our clusters. So let me go ahead and get this code here. But now we're going to add some colors. So here I'm going to have the original plot, but I'm going to say color equals model.labels. So we run our model and stored it in this variable called model. And then it has an attribute called labels, which is going to be which category it's in. And I'm going to just kind of format this to be a little nicer. So now, as you can see, we have 5 clusters. I guess the color it chose for this cluster right here is horrible because it blends in with the background. But if we go up, you can see there's some points down here. So we have a green cluster, a yellowish cluster, a red cluster, a horribly like white, purple, very bad colored cluster, and then a blue cluster. And so this is probably appropriate, but like Matt said, there are like ways we can use to determine whether this is the appropriate number of clusters. So let me show you how we might want to do that. So there's a map that we can make. I think I have code for this somewhere, so let me just try and pull it up. Because there's no point in typing it all out if I have it somewhere. Okay, I think it's this. So we can run a graph which shows us, it looks like this, and it shows us on the y-axis the sum of distances of points to the closest cluster centers. And so each of these clusters has a center. It's called a centroid. So a center of that cluster, which kind of defines like the middle of that cluster, or like what everything is clustering around in these different points. And so like as we get further away, as the distance increases from the cluster, that means it's less likely to be like part of that cluster for real. And so as we increase the number of clusters here, each point has more opportunities to be closer to some center. And so the distance to the closest center decreases. But we just want to have the right number of centers. And so that means we just want the reduction in this right here on the y-axis to be very small. So where the plot seems to like start flattening out, that's the appropriate number of clusters. So here we can see it starts flattening out at 5. And so we can make this graph, and wherever this graph starts flattening out, which is about 5, that's the appropriate number of clusters, which is kind of what we did. We could change this to be like 4 clusters and see what happens. So here it looks like it grouped these 2 together. So we have 1, 2, 3, 4. But as we can see here, this curve here is still kind of flattening out when we have 4. And so we would probably want to use 5 clusters. So I'll go back and change this to be number of clusters equals 5. So yeah, there's a few different ways to do it, but this is one of the ways, and we use the distances of the points to the center of the cluster. We make a graph of that, and wherever the graph flattens out, that's probably where we would want the number of clusters to be. Did that answer your question?
Yeah, that was fantastic. Yeah, the final approach is what I was looking for. I can't remember what I was doing, but I had a lot of data, and yeah, it was a plot just much like this, except I think it was I think it was different. It had like a sort of a U shape, and you wanted to pick the apex, I think. Doesn't matter. That was great. Thank you very much. I'm sorry for derailing you. Let's get back to your planned session, but thank you. You're very intelligent.
Okay. Awesome. Yeah, thanks. Oh, I hear a little reverb. That's strange. But yeah, no, that's a great question. And it was a little more advanced than what I was thinking we were going to get into. So I actually appreciate you for asking, because it's kind of fun to get into this stuff. And actually, let me just take a screenshot of this right here. And I'll put it in the chat so that you guys can have it really quick. So I'm just going to say how to determine the appropriate number of clusters in clustering. Just so you all have that.
That might be, I mean, this is just an observation, but it might be cool to work that into the class somehow.
Yeah, that's a great point. Yeah, I agree, actually. Okay. Let's see where we are. Okay. So now that we've done that, and we've even talked about how we might choose the appropriate number of clusters, let's apply it to an example. So our example here, I think this is going to be a little more fun because now we're actually using images. So as you can see here, we have some images, and they're even poor quality, probably because it's so zoomed out. They're probably supposed to be much smaller like that. But when we make them big, they look very pixelated. And so they're images of handwritten numbers. So what we're going to do is we are going to try and group these into clusters based on their number. So we're going to try and get our algorithm to correctly put these into groups. So we want all of the zeros together, all of the ones together, all of the twos together, etc. And even though it's not going to know that these are numbers, it's going to look at their characteristics, which is the color of each pixel, actually, to try and predict. So there's 3 steps. First, and really only 2 main steps. First, we'll pre-process the data. And second, we'll run the k-means clustering algorithm. And finally, we will plot the clusters. So the reason why we weren't doing the thing before with choosing the appropriate number of clusters as a part of this example, and why I had to pull out that separate data, is because in this example, it's very obvious how many clusters we want. We want 10 because we want 0 through 9, which is 10 different numbers. So we already know we want 10 clusters, so we don't have to go through that process. But sometimes it's not quite as obvious, and we might need to make some decisions about the number of clusters. And so that's when we would need to do what I was showing you all before. But here we don't need that because we know we want 10 clusters, 1 for each number. So let's go into our collab file. Okay, and 3, k-means. So we're in unsupervised learning clustering. So you'll notice there's not a CSV file here because this data actually is from a library, and it's in the sklearn datasets. And so we can just get this straight from Python. We don't need to download any data, and I thought that was easier. So we are going to get this load digits, and we're going to call it digits. So in load digits, it's just a bunch of handwritten images, as you can see. And so here, what I've done is we're just creating kind of a little subplot to show you one of each of the numbers here. So we're just loading in this data and then kind of printing out a picture of each of the options. So you can run that. And like I mentioned, we want to put them into groups based on the numbers that they show. But how does a machine read handwritten numbers? Like, we know that a machine can't just look at a number and in the way that we as human beings would do say, oh, that's a 1. So what it's doing is it's converting each of these images into a 2-dimensional matrix of pixel values. where 0 represents the black pixels and 1 or anything closer to 1 will represent the whiter pixels. So 1 would be the absolute white, and then the ones that are closer to 1 are going to be like the lighter grays, and the ones closer to 0 will be the darker grays. And so you can kind of see these are pixelated, and these are the pixels for the first image. And so we know this is the first image because I'm looking in my data and I've indexed the first one based on the number 0. So we can see here, this is the two-dimensional matrix of pixel values. So yeah, the ones that are closer to 0 are the black ones, and the ones that are closer to 1 are the white ones. So the first step that we want to do is pre-process our data. And there's a few things we want to do. First, we want to scale our data because sometimes there are pixel values that are more important to notice than others. So for example, if we look at these images here, is there something you notice about the very top left pixel of basically every number? It's all black. The top left pixel is black in almost all of these. And so if that top left pixel were to be white, that would be a really important feature because it would make it super easy to categorize that image. And so we would want to make that much more important in our model. And so we can kind of weight the different features differently. And so that's what we're going to do with scaling. We're going to say, okay, if there's a feature that's a lot more important in determining our prediction, we want to make that more important to our model. So that's what we do with scaling. And we just import scale from sklearn. And then we apply that to our data. The second thing we want to do is shuffle the data. And the reason is this. If all of our images are ordered in numerical order, so if it's all the 0s and then all the 1s and then all the 2s like that, it might start picking up on little differences between the same numbers instead of picking up the important differences like the difference between a 0 and a 9. So we want to shuffle it up so that we're not making our algorithm start to look at the differences between all of the same numbers instead of the ones between the different numbers. Is it clear why we need to do that to you all?
Yes, I drifted off. But yeah, thank you. And
Awesome.
I to say, last comment about incorporating into the class, didn't mean to be critical or negative. You're awesome. You're doing a great job.
Oh yeah, no worries. I always love feedback because it's always good to make these better. So that's great. Awesome. So yeah, we have our data pre-processing done. So let's run that. And then we're gonna just make our model. So we need to, of course, import our model as always. And again, when talking about the number of clusters, we know we want 10 clusters because there's 10 numbers, 0 through 9. And so n clusters, number of clusters will be 10. Okay, so we run this, our model is created, and we know this k-means.fit is what actually creates our model. Notice we didn't do anything with training and testing sets because all of that is what we do when we have labeled data in supervised learning. We don't do that here because this is unsupervised learning. So instead, our model is done. We can plot our clusters. This one will take a while to run, probably. Because we're trying to render images based on our model. Okay, and now it looks pretty good. We have some different clusters. And again, the number of this cluster doesn't necessarily correspond to the number itself because it doesn't recognize these as numbers. It recognizes them as grouped images. So we can see most of the 4s are in this one. We can see it got all of the 0s, right? The 0s are all together. The 9s are mostly together, but it got some 3s in there. The 7s look pretty good. The 6s look pretty good. The 1s look okay. I think that might be a 7 or maybe a 2. So overall, it did it pretty well. But as we can see, we as human beings would still probably be able to do a better job than this model. But we can always make it get better and better over time. But this is just kind of the first model. And then we can apply it to new data that we get too.
That was a really cool example. I don't mean that. I know sometimes my inflection isn't good. Can you go through the shuffle the data again under step 1 data preprocessing?
Yeah, for sure. So before we run our model, we need to shuffle up our data because, and maybe let me go into the PowerPoint. So if I have a zero, actually zero is a bad example. Let me try with like ones. If I have a 1 that looks like this, and I have a 1 that looks like this, and I have a 1 that looks like this, and I'm getting a little reverb. But if I have ones that look like all of these things, if all of the ones are in order, and then the twos, if they're all ordered like this, it's going to start looking at the differences between these two ones and start treating them as different numbers, even though they're very similar, because it's only seen these two when we first start. So we want to shuffle it up. We want our data to look like 1, 9, 3, 4, maybe another 1. It's random. We don't know how it's going to shuffle, but we want it to have different numbers next to each other so that in the beginning, when it's only seen a few, it's able to distinguish the different numbers rather than classifying the same number that looks a little bit different in different groups.
Fantastic. Yeah, thank you. And that way, each iteration, it learns more.
Exactly. In each iteration, it learns more. Exactly. Great question. Let me stop my screen for a little bit. How are both of you feeling about these algorithms? Is there anything you want me to go back and look at?
The walkthrough, I understood it.
Okay, great.
I can't say I can do it for myself, but I understood as you explained.
Yeah. No, and that's kind of the purpose of like this workshop specifically, because we can't just like, learn all of machine learning in like 4 hours. That would be impossible. So what we just kind of want to do is like get a good conceptual understanding of some of these algorithms and see how they can be run and applied. The goal isn't necessarily that you should be able to do it on your own just yet. Yes, and then let me see here. So I think based on both of your experience levels and like how well you did with today, this workshop was technically a way for you to test out if you would be interested in our Intro to Data Analytics class. But I think both of you are way more advanced than that and would be really great. We have a data science class, and let me show you that. Okay, so yeah, we have some different courses. I teach the intro one. We also have this advanced one, which is called Learn Data Science. And it's a lot focused on these things. And so you'll go much more in depth into Python, machine learning, predictive analytics, prescriptive analytics, and data collection, visualization, and things like that. So it's a lot of what we did today, as you'll see. Like there's a whole week dedicated to supervised, unsupervised, and reinforcement learning at the beginning of the course. And it's 12 weeks, and it's like after work times, and so it's like this isn't Pacific time. So for me in Central Time, this is it starts at 7, but it's split into like lectures and labs where you have time in order to just like learn from a lecture and then time to go ahead and practice it on your own and make sure that you have the concepts mastered. But it's basically just 12 weeks of getting really into this. And so by the end of that course, you would be able to do all of this stuff on your own. And like it's a really great course. I know some of the people who have been involved in it. Yeah, there's even like individual weeks dedicated to like classification, regression, things like that, and a lot more in depth than we did today. And so I think probably both of you would be like exactly where you need to be in order to get the most out of this advanced data science class that Skillspire offers. So I can put this in the chat if you want to learn a little more.
Yeah, put it there. We have to take a look at it.
Can you take a quick look at the less advanced course as well?
The less advanced one?
Yeah, please.
Yeah, for sure. And I can tell you a lot about that one because that's the one that I teach. Let me show you. So here I'm on the website and I go to courses and then I go to Intro to Data Analytics and Data Science. So Jeff, he's currently helping me out with this current class that I'm teaching. It ends in like 3 weeks and he's great. He'll be teaching the next one that starts in just a few weeks. In that class, we do Excel, we do Power BI, we do SQL, we do Python, and we learn how to incorporate ChatGPT into our analytics problems. And so we do Excel for the first part. We do SQL, so we do a bunch of database stuff in the middle, and we do that for several weeks because it's a super in-demand skill. And then we move on to a little visualization in Power BI. And then we're finishing out the course right now in the one that I'm teaching in Python, where we get a basic foundation of Python programming, as well as doing some analytics things in pandas and stuff like that. But we don't quite get into like machine learning or anything like that because that's more for the advanced course. And so the next one for this one starts July 17th, which is very, very soon. And it ends September 13th. And so it's a 12-week course that meets after work hours. But there is another one too that starts in November and ends in February. And here are the times for that. And I can link this one in the chat too. And these are also online courses. I think Skillspire offers some in-person and some online courses. I believe, I know for sure that the intro course is going to be online, and I'm pretty sure too that the advanced one is going to be online. Because like I don't even live in Seattle where a lot of these classes are, so I know a lot of the instructors live remotely too. So I think remote classes are pretty cool.
Definitely.
Awesome. So yeah, those are the two links there. We offer like more courses on like other software engineering concepts. These are just the two courses that are in the analytics field. So yeah, so those are, I do think though that both of you would be very well equipped for the advanced one. But if you have any friends that you could refer to the intro one that they might enjoy, I know it's a great class and I love it because I teach it. But yeah, do you guys have any questions on anything that we covered today, on looking for jobs in analytics, on the algorithms, or on anything in general? Because we have 40 minutes left that we can dedicate to talking about whatever you want, or we can leave at whatever point.
No questions, really.
I think there's a little like reverb coming back from one of you.
Yeah, it's my fault. It's mute that.
Okay. Dawson, did you have a question?
No, I said no questions. No questions, really.
Okay.
You know, I mean, it just seems like the analytics market is a little tougher out there, especially in my market. I live in Georgia, and I'm contemplating whether I want to move out of Georgia, which there are more opportunities if I do, but like, you know, I'm kind of grounded here. Like, you know, I just recently bought a house and all that, so it's like, you know, it's kind of a toss up for me what I'm gonna do. But it's been a challenge here in Georgia. It's like the market is, with all the layoffs, the market has gotten so competitive with most people wanting 3 and 5 years experience. So, you know, that's the problem I'm facing now. That I think if it continues this way in the next 3 to 4 months, I'm gonna start exploring out of Georgia, which is actually my last resort.
Okay. And one thing I will say, feel free to like apply for jobs, even if you don't have like the number of years experience that they say that you should have. And also like if you're like exploring things on your own time, I would still consider that years of experience.
Okay.
Like for example, I think like I need to find a statistic, but like a lot of times it's only really expected that you have like maybe roughly 70% of the qualifications listed on job postings. I learned that in business school. It was crazy. Like you don't actually have to meet all of the requirements. You should probably meet most of them, but if you don't meet some of them and you can kind of explain why, sometimes that's okay too. So just go ahead and like apply for them, even if you feel you aren't completely qualified. Because my last consulting job, I only met like 70% of the requirements and I got the job. So sometimes you'll be surprised.
Nice, nice.
Yeah, cool. Any questions from you, Matt?
No, I'm just looking at how the final plots of the clusters are done for the numbering example, and it's a little beyond what I usually would do. Probably something I could do if I took some time, but actually, I don't even know if I could do this if I took some time. I wouldn't even know where to start to create this plot. So, and I don't think that 40 minutes is gonna cover it, but you really killed it here. That's cool.
Awesome, thank you. And in terms of the plot, like you don't necessarily need to know how to like create these from scratch, because if you're doing clustering again, you can just reuse this and change it based on the number of points that you have. And that's a lot of what coding is.
Stack Overflow.
Stack Overflow, absolutely. Probably where I got this originally, if I'm being honest.
Man, if they monetize that.
What was that?
They figured out a subscription model to Stack Overflow.
Wait, they have one?
No, I'm saying if they did.
Oh yeah, I was like, oh no, it's not free.
They would be the richest company in the world. It would be awful, but
The Stack Overflow is owned by Microsoft. They already have enough money.
yeah, it's true.
Wow,
They
I
need,
didn't know
they
they were
need to
owned by
give us
Microsoft.
something for free for all the stuff we pay for.
Yeah.
You mean all the shoddy products we pay for?
Man, I'm surprised. Like this is the best. This is the best time I've been on Teams where it actually worked without any issues. Like I've never had that experience. And I just left my job like 3 months ago, and I use Teams like 4 or 5 times a day, and it was always some issues.
Yeah, but I mean, thank God for having Teams before COVID, right? I mean, for everyone that worked remotely during COVID, man, without Teams, that would have been a nightmare.
Yeah.
It also would have been even more super isolating.
Absolutely.
So, I don't know. I'll bash them because it's not a bug; it's a feature with them. But thankful for them.
Yeah, absolutely.
Indeed. Yes. As bad as we talk about them, like I'm thankful for them. Right? Even for me, like I've used Power BI and Tableau, and a lot of people say they prefer Tableau, but I prefer Power BI.
Wait, which one do you prefer?
Power BI.
Yeah, I do too. As much as I hate to admit it. Okay. So I will put my email in the chat in case you have like any questions later or anything like that and want me, or like if you are looking through the code and get confused or something like that. Also, if you want access to my slides, I can email them to you because I don't think this chat is equipped for like file sharing. So if you want the PowerPoint slides, just put your email in the chat and I can email them to you in a few minutes. And other than that, like if there's any more questions, yeah, just feel free to email them to me. But we can go ahead and end early if there's nothing else that you all want to cover.
Good. You've been awesome. So thank you so much.
Awesome. Thank you. You guys are amazing. So I will email you those files in the next like 5 minutes. And I look forward to hearing from you if you have any further questions.
All right. Thank you so much.
Awesome.
Thank you again.
Bye.
Have a fantastic day. Bye-bye.
Yeah, thanks. Have a great weekend, guys. Bye.